See a couple of familiar faces. Hopefully by the end of the next day or two, we'll get to know all of you. So this is the SEG disc. So each year the SEG sends somebody around to talk about a topic of interest. Generally it's hydrocarbons, but most, and particularly with respect to seismic analysis work. But in this case, they've chosen a different topic and me, so we're going to talk about electromagnetics, both the fundamentals and the applications. Before I start, as we're traveling around the world, and you can appreciate, so we're in Canada, we're trying to make contacts from countries that we've never been to, organizations that we've never been. And really it all depends upon the local host. And in this case, both Daniel and Diana have been absolutely superb in organizing this and making sure that the registration somehow gets through in spite of the SEG, and that courses can be offered at a reasonable rate, and hopefully everything will go smoothly. Anyway, I thank both of you right on behalf of both Lindsay and myself from the bottom of our heart, because otherwise this just wouldn't be happening. I thought we actually might start off, it would help me a lot if we kind of went around the room, and if you just briefly introduce yourself, just your name, kind of where you're from, and you're interested in, what your interest is in electromagnetics. That'll help me actually set the scene, because I need to know if there's some people here who have like very small amounts of background, or medium, or large, or just to kind of put everything in perspective. So let's start at the back.
Hi, my name is Eduardo Barcon. I'm from Venezuela, but I have like 3 or 4 years of work experience here in Chile. I'm working for a company, X, mainly in DC resistivity and different other methodologies of the physical perspective.
Okay, good. Next.
Hi, my name is Monica Paulini. I'm a geophysical engineer, and I'm working in AWEX.
You're working what?
In AWEX.
With it's a consulting.
Okay.
Company.
Yeah.
Hi, my name is Esteban Diaz. I'm studying geophysics. I'm finishing my master's degree. That's that.
Okay, great. Fair enough.
Hi, my name is Santiago. I'm a geologist. Most of my experience in exploration, so the idea is to learn something about geophysics. What to need to use all the tools.
Perfect. Okay.
Hi, I am Daniel Diaz. I am part of the organization. I'm Manuel Alvarez. I'm a hydrogeologist. I used to use some geophysical techniques of some water exploration on conceptual modernization.
Oh, good.
Hi everybody, my name is Juan Correa. I work too as a hydrogeologist. My background is a little bit slow in geophysics, and I'm willing to know a little bit more to apply in the field.
I'm a master's student here. I'm finishing my master in NTS method, and I know in some electromagnetic methods.
Okay.
Hi, I'm Nicole. I'm getting my master here in geophysics too, but in a different topic in geodesy. But I'm interested in these electromagnetic methods because I'm not too familiar with them. So.
Yeah. Hi, my name is Alice. I'm from Venezuela. Now I'm working in a very small company. For the moment, we only apply the GPR service. We want in the future apply another techniques to physical techniques. My name is Brendan. I'm from Canada. I live here in Chile, and right now I'm working with PHP. And my experience is mostly in airborne geophysics. So I'm excited to learn a few things about the ground.
My name is Camila Leighton, exploration geophysics working for PHP. And I'm excited for this.
Hi, I'm Natalia Diaz. I'm a student in the geophysics department here, and I'm interested in learning more about these techniques.
I am Fernando Zamudio. I am a physicist and geophysicist, and I start my life of professionalism with electromagnetic view as the astrophysical point of view, and then I went into geophysics, and I really like MT and IT.
Hey, I'm Francisco Ortega. I'm a professor here at the Department of Geophysics. I'm an expert in inverse methodologies and geodesy applied to active tectonics. I'm here because I have a student, co-guiding student with Andrei Maximowicz, that he will be using aeromagnetic data. So I'm helping with the inverse method parts of his work.
Good morning. My name is Fernando Rodriguez. I work in a geophysical prospecting company. I work in basically in electrical field.
Terry.
Terry Ritchie. I do have a degree in geophysics. I work in a contracting company. We provide IP and M2 servers, so we don't really need to have much steering.
I am Jimena Vargas. I am a geophysicist and I work at GRS with Terry. Same company.
Libby Shaman. I'm with BHP. I'm one of our principal geoscientists in charge of our global crop research. I don't have a massive geophysics background, which is part of why I'm here today to learn a bit more about an aspect of geophysics.
Hello everyone, my name is Hector and I work for Terry and Jimenez. We are the industry. We work in most of our work, it's based on NT, DC and IP. And I'm mostly, much of my work is related with processing data. That's all.
Hi, Eddie Roberts, geophysicist working with various American exploration programs. I guess my background is a little more geological as well, so I was sort of keen to just go down some of the programs.
Hi, I'm David. I am a master student. I am the one who is trying to improve some high-level fields.
Hi, my name is Gustavo. I'm doing the Master in Geophysics here, and I'm working with Daniel in Chile.
Hi, my name is Daniela, and I'm getting my master here, and I'm working with Daniel too. I'm making a research with transient electromagnetic. So that is what I'm here.
Hi, my name is Ariel Figueroa. I'm a student in geophysics. I'm working with Daniel. I'm working in my thesis with MT.
Hi, my name is Felipe Zuniga. I'm studying here a master degree in geophysics. I'm going to study with.
Hello, I am Santiago Mundes. I am a master student. I am working in seismic reflection, but this could sound very interesting.
Oh, good. And we just had 2 people, and now 2 more coming in for the back. If you just quickly introduce yourself, tell us what your background is and what you're doing. Sure.
I'm Mr. Victor Castillo. I'm a geologist. I'm working as geophysicist.
Good.
Hi, I'm Francisca Quiroz. I'm in geophysics. I'm working on geodatos
Okay, and is anybody else?
I'm Valentina. I work in GRS as well, and I'm also a geophysicist.
Okay, and maybe others. Yeah, one more.
I'm Felipe. I'm a geologist, and I'm interested in getting a master's degree in geophysics.
Okay, excellent. Okay, I appreciate that. So we've got a whole host of backgrounds. We've got people here who know very little about electromagnetics. Some people know something about something, DC resistivity or magnetotellurics. Other people are perhaps expert in some parts, but maybe missing something else, whatever. I think the goal for today is to try to kind of bridge all that gaps, and what I'm going to try to do is provide at least something for everybody. Unquestionably, there's going to be parts that we're going to see you're thinking, oh yeah, well I know all that, but maybe there's going to be stuff that you haven't seen before. But before we start, since you've told me a little bit about yourself, I'll tell you a little bit about me. So I went to Scripps Institute of Oceanography, did my PhD there, was mentored by Bob Parker, Freeman Gilbert, and George Backus. Those are probably the three big names in geophysical inverse theory. These are the people who really started to set the inverse problem in the way that was mathematically tractable. Just to give you some insight of where we were, this is a timeline. It goes from 1975. If you look at the kinds of problems that we could solve then, it was maybe the 1D DC and MT problem, 50 variables. Later on, 1985, we're up to 2D at this point. Now we can handle maybe 1,000 variables. By 95, we can solve the 3D problem for simpler problems, the gravity, mag, DC, and IP, 10 to the 5th variables. About this time, 2005, there was two things that came about that were really important. Up until that time, we could solve maybe the 3D frequency and time domain EM problems, but with maybe just one or two sources. And then what came about was the ability to take a big matrix and factor it. And if you could factor the matrix, then you could actually solve many right-hand sides or have many processors. So I'm going to see if we can get that other pointer going. This one's dead. That allowed us to solve problems with many sources, and then you put that with the ability to have multi-cores in a computer, and you've now got the opportunity to handle very large-scale problems. And today, I think we're in a position that we can invert 3D frequency and time domain data with lots of sources. So the bottom part about this slide is that with the advances in both computing power and background in inversion theory, I think we can pretty much solve every EM problem that is currently around. So in addition to that, there's been, oh, that's good. Major advances in acquisition of data, instrumentation, and the quality of data, so that we can now get data, unprecedented numbers, unprecedented quality. And that is actually what's been required in order for us to take that next step as far as using the data. And so there's sort of large-scale groundwater studies in California, in Australia. They've got a magnetotelluric project called OSLAP, where they're going to acquire MT data over the whole of the continent. And offshore for the oil industry, there's marine CSEM that is used to help de-risk a well. In other words, to try to find out whether a particular region down here has got good hydrocarbons or is just fluids. But that requires massive amounts of data and high quality. A third thing is, and we've really seen it in the last few years, is just the development of open source material and web-based material that allows people to collaborate, to share, test changes, kind of interactive computing so that you can work together. There's been an initiative at UBC called SimPeg. So this is a programming package, or environment for carrying out simulating, forward modeling, and reversion of geophysical data. And that's open source software, and it's built in Python. We'll talk quite a bit more about that, especially tomorrow. But all the examples that I'm going to show you today, most of them at least, have been developed here. And then there's GitHub, ways of storing data, keeping track of version control, and interacting with people. So that's a huge change over the last few years, and that is also promoting a bit of a paradigm shift in how people think and work together. And lastly, I just want to say that there's just a huge number of applications. Electromagnetics can be used for mineral exploration, certainly some of that here. Contaminants, issues with water, geothermal energy, unexploded ordnance, hydrocarbons, slope stability, and geotechnical problems, and the list goes on. And I think one of the things that we'll see today is that for a lot of these different kinds of problems, electromagnetics has a role to play, and we can actually do that because of all of the advances. So we've got the basic ingredients. We've got problems, we've got high quality data, we can invert the data, and we've got the web tools to communicate. See, seems like we should be good to go. So what are the roadblocks? Why isn't electromagnetic geophysics being used daily to solve all these problems? Well, there's actually a lot. I think one of the biggest is, in general, geoscientists, they often don't realize the role that EM can play in solving their problem. And then they don't really understand the technique. The terminology is a bit confusing. You know, people start talking about real data or imaginary data or something like this, and you know, people are like, okay, what's that, right? And then the other thing is that electromagnetics, it's complicated and it's unintuitive. So it's not like seismic where you just see, you know, you could visualize it. You got an idea. Okay, wave goes down. There's an impedance contrast. Something gets reflected up, and I see it. And I just look at a map of the data, and I can make a geologic interpretation. Unfortunately, you can't do that with electromagnetics. You cannot look at data and somehow interpret geology directly from that. So that's an issue. Another important thing is like, what's the connection between my problem and the physical property that I'm interested in? You need to really define that. And then even if you do decide to use this, it's a question of, okay, there's so many types of surveys, what should I use? Should I do something in DC? Should I work in frequency domain, time domain? And my surveys should be, are they on the ground, or are they in the air, or down the hole? And what should I expect for resolution? And maybe lastly, the thing is, and this gives you generally great comfort, right? If you have a problem and you can find that somebody else has actually used EM to solve a problem similar to yours, you've got now kind of a template, and you know, you feel a little bit better about it. But in general, those are the roadblocks. And you know, I think my task for today and tomorrow is basically to let's just get rid of those. So that my hope is that by the end of tomorrow, most of these things will just be kind of crossed off your list, and you'll just feel much more comfortable in going ahead and using electromagnetics. So here's the disk, right? And it seems like there's a perfect storm out here. We got problems, we got good data now, we can invert anything, we've got web tools to communicate. And so we should just have the disk, put it all together, and get moving. But there's an important ingredient that's missing. Anybody tell me what it is? Us, exactly, you. So that's right. So we need to have that next level of brilliant scientists out there that can actually do the work, so that when the old guys like us can't program very well anymore, there's guys like you that can go ahead and do that. So here's two people. One is Sagi Kang and the other is Lindsay, who's here. They've been both co-presenters for the disc as we've been going around. But really, that missing element here is the thing that just completes the circle and should make everything go. So what are the goals for the disc? Well, first of all, I want to inspire you. I'm going to do that by showing you a variety of applications and illustrate the effectiveness through case histories. I want to build a foundation. I cannot overemphasize the importance for you to understand just some fundamentals of electromagnetics. By understanding the basic principles, you won't make mistakes that have been made, time and time again, in trying to adopt some bogus technology that doesn't particularly work. And we're going to help understand those principles by working with a bunch of apps. So these are Jupyter notebooks that allow you to have sliding bars and explore, ask questions, and kind of see the results of fields and see if you understand the problem. And then we've got an open source resource, GeoSci. When SEG puts around the disk, they always ask that the presenter provide a book. And we could have done that, but we realized that the moment that you write a book and you put it to press, I think it's probably out of date. So what we've done is developed an open source resource that will continue to grow with us and later on after we're finished. And we want to set realistic expectations for what you might get out of a survey. And a big item here is we also want to promote the development of an EM community. We want to be a bit of a catalyst here and do that by collecting together with open source software and then just capturing case histories worldwide. I don't know, how many people have seen that cover on the left side? How many? 2, 4, half a dozen. This is a cover of a book published by the SEG maybe a couple of decades ago, edited by Misak Napigian. There's a chapter in there by Warden Homan, which is kind of a Bible for most students who come through geophysical electromagnetics. It's really well written. It's got all kinds of derivations and solutions and things like that. And it's been really useful, but it's hard sometimes to grasp what's really going on when you're just looking at equations and maybe occasional cross sections. So what we wanted to do was to take this book and make it live. And so here's our resource. Looks like this. There's some background material on various kinds of states of Maxwell's equations and time, frequency, DC. There's a section on geophysical surveys, a bit of version. And then there's case histories. So case histories are presented in a form that looks like this. We're going to do that throughout the whole day. Each case history is parsed down into a 7-step performance. I think anybody who's doing applied work would realize, like, okay, these are pretty reasonable things to do. And the first is, what's the question? What is it that you really want to have answered? And then, what's the physical properties that are associated? What survey should I use? What's my data? What processing do I apply? What's my interpretation? And finally, your synthesis. How have you impacted on the solution of the problem? This is a nice way of parsing things down. It also is a great way to promote interaction, because if you have a problem out there and we're trying to communicate and interact, if I know where you are on this scheme of things, it makes it really easy. So rather than you handing me a book of 50 pages of stuff, parsing it down into something that's just the essence of what you're really trying to do where you are really promotes that interaction. And all of this stuff can be edited. So we put it on GitHub and just sign on to it on web, and there you go. And why apps? I take an equation like this. These are two Maxwell's equations, and they're incredibly important. But if you look at them, they don't really tell you very much. Somehow we've got a time varying magnetic field relating to an electric field and a current relating to a magnetic field, but it doesn't really tell you that much. But the moment that you take that and you put it into a sort of an app that gives you some parameters that you can change, change the conductivity or the frequency. What this app is an electric dipole in a homogeneous space. So this is the fundamental type of source and experiment that's used for control source EM, for instance, in the sea. And what you're looking at are field lines here. But by being able to adjust parameters and see what the results are, that can give you a great deal of insight. So we'll be showing a lot of apps as we go through. So goals that we want, well, we first of all got to connect to relevant applications. Then we're going to select a type of survey, use the apps, kind of explore, ask questions and explore, and then we'll show the success through case history. So we're always going to tie things in a practical outcome. So the agenda for today and for tomorrow, so this is a 2-day affair. In some cases, we've actually been forced to provide most of the course material, in fact, all the course material in 1 day, which makes it really hard for everybody, people listening. Because I tell you, especially for people who are not very familiar with the stuff, then you're trying to assimilate things. And honestly, after like 8 hours, you're just blitzoed, right? You can't absorb anything else. So what we'll do for the course material is we're going to divide it into 2 days, or at least a day and a half, and then have the second part of tomorrow be devoted a bit to other things. But here's what I want to do, and here is why I want to do it. Because I don't think this is, to my knowledge, I don't think anybody's really ever done this before in this kind of a condensed time. We want to look at electromagnetics right from the get-go. Just do the simplest experiment, which is a DC resistivity experiment. Then we're going to look at the fundamentals of electromagnetics. We'll look at inductive sources. And we're going to look at both in the time and in the frequency. And one of the things that you're going to also see by the end of tomorrow is that really, there's really no difference between time and frequency. When you look in a book like Ward and Holman, the first thing they do is they do everything in frequency, and then, okay, having done that, now they look at time domain. And it almost seems like it's two different things, but really, they're basically the same, and we're just going to be flipping back and forth, and by the end of tomorrow, you're going to just be completely comfortable with time, with frequency, and see how they connect. Then we're going to extend it to grounded sources. And that'll take us about today, getting through there. Then pick it up with natural sources, that's where your MT comes in. And then high frequencies, that's the GPR. And then induced polarization, the fact that the physical properties could be dispersion. So that's an ambitious schedule, and to say the least. And there's a wide variety of topics, but I hope there's something here for everybody, so that when you come away, you feel like, okay, I'm really, really glad I took 2 days off to interact with this material. But, we're not really targeting the experts, but even for them, I would hope that this might be interesting. So my wife and I go for coffee every Saturday morning. We go to the same coffee shop, we go to the same people, and 9:30 every Saturday morning we meet. And we've been doing this for 23 years. It's a long time. Every time we go in, there's a new saying on the wall. So then Ray's quote. And this one I thought was particularly appropriate. It says, "That is what learning is. You suddenly understand something that you've understood all of your life, but in a new way." And if that actually happens, that enriches your understanding, and enriches your creativity later on because you just have a different way of thinking about it. So maybe that also. But the disc is a 2-day event as far as the SEG is concerned. It's 1 day because it's a struggle. But second day is really sponsored by GIF and ourselves. But tomorrow afternoon, okay, what we want to do is to have more what we call GIF Lab. We'd like to have you tell us what the problems are that you are working on. Just briefly, couple minutes, few slides, just like, okay, what kinds of problems are you working on? We've been doing this around the world, and it's been really, really interesting. Every country that we go to has got a suite of different problems that they're interested in. I mean, if you go to Europe, for instance, they're not interested in hydrocarbons, they're not interested in minerals, but they're interested in water issues, geothermal energy, pollution, right? You go to some other countries, and really they're mostly hydrocarbon and minerals. And so it just depends where you are. And here we go around, we capture these, they're put up onto YouTube, and it's then a permanent resource for anybody asking, like, okay, what kind of problems are they doing in Chile? You could look, and you'll get a suite of them. So we're going to about 30 locations around the world. Each time we capture 5 or 10 of these. So it gives you quite a suite of problems, and also gives you people to connect with. So again, we're talking about the community. That's one way of developing it. And as far as connecting, has there anybody used Slack? So this is a very nice way of interacting, asking questions, sharing information, and yeah, you could try joining a Slack channel and asking a question and see the community. And then there's potential contributions to GeoSci through case histories, as well as the software through Symphony. Okay, so that's sort of global background. Let's now start with getting on with EM. Here's 3 problems. We've got a minerals problem, try to find them. Maybe we've got an unexploded ordnance problem, which definitely exists in some places. And we've got maybe water problems. I chose these problems because each of these at a first glance is kind of connected with a particular physical property, something to. The first property I want to talk about is electrical resistivity, or its reciprocal conductivity. Electrical resistivity is something that tells you how easily it is to pass a current through some kind of material. And the resistivity is in ohm meters. And this is a scale, it's a logarithmic scale on top, so it's 8 orders of magnitude. There's some rocks that have very low resistivity, massive sulfides, for instance, graphites, or saltwater. And there's some that have very high, so igneous rocks, limestones. There's a lot of stuff that's just kind of in the middle here, various clays, tills, hydrocarbons, for those who are interested, sort of 100 ohm meters. The reciprocal of resistivity is conductivity. So here's the scale here. So anything that's got a high resistivity, it's got a very low conductivity, and vice versa. As I talk, and as most geophysicists talk, the words conductivity and resistivity are just used interchangeably. And you just kind of have to get used to the fact that flipping from one to the other. Dielectric constant, effectively relative electrical permittivity. Air is 1 unity, and then fresh water is 80, and interestingly, seawater is also 80. So it's just the ability for molecules to polarize under the action of the electric field. And everything else is kind of in between. So this is going to become important towards the end, well, actually tomorrow, when we do ground penetrating radar. So this is the physical property that's important. And magnetic permeability or susceptibility. again, can vary by orders of magnitude, with magnetite being the most susceptible. In other words, on the application of a magnetic field, the rock that contains magnetite will acquire the largest magnetization, and other rocks sort of are kind of scattered all over the place. But interestingly enough, you notice that irrespective of which physical property I have, if I took a particular value, it could correspond to a whole range of rocks. So there's no unique fingerprint by knowing what a susceptibility or conductivity is of deciding which rock that is. The general cartoon for doing geophysical survey is that, okay, we've got a source, we're going to input some energy into the ground, and here is 3 physical properties, and then we're going to measure some data. So that's sort of the basic idea. Here's our equation. This is not going to be a mathematical course, but we're going to see this particular slide a number of times because it tells us, well, these are Maxwell's equations. So first of all, there's this equation here. It's called Faraday's law. It says if I have a time-varying magnetic field, I'm going to get an electric field. This upside-down triangle is just something called a curl operator, which means that things are going to be circular. Ampere's law says if I have a current density, a current, then I'm going to get a magnetic field. Then there's also constitutive relationships. So these are things that have actually been measured in the lab that relate, say, the electric field to the current density via a physical property of conductivity. So this relates a field with a flux. Same with magnetics, same with dielectric constants. Fields can be written in lowercase, which means that they're going to be time. And if I take a Fourier transform of these, then I get similar equations, but with capital letters, so those are going to be in frequency domain. Let's just think about sources, right? So here is our cartoon. We need a source. We're going to measure these properties, get some data. So what kind of sources could I have? Well, I could have like just a loop of wire that's carrying a current. So we're going to use that as an inductive source. I could also take a generator and attach it to 2 probes, and now I'm pumping current into the ground, so that'd be a grounded source. It's good I have inductive and grounded sources. Good. The next thing is, okay, what kind of a waveform do I want to put through? Well, I could put through just a harmonic, and usually we refer to that as a frequency domain signal. I could also put through some kind of a transient, might look like this, has on time, maybe an off time. And that would be a time domain signal. And finally, then the location of these transmitters, where are they? Well, they could be in the air, they could be on the ground, or they could be underneath. So those are our options. And it's interesting, I have to be careful if I touch the screen, because I have no idea how the screen works. But evidently, I can touch this screen in various places. We can draw cartoons or whatever. We might experiment with that. So those are options. And what about data? Well, what could I measure? I could measure an electric field. I just put down 2 probes and have a voltmeter here. Or I could measure a magnetic field. So I can make it E or B, or in the time domain. But then the question is, okay, well, which frequency should I measure? Or in the time domain, which times do I really want to measure? Is possible. And then also components. And where's the location? Where are these guys? Where am I supposed to put them? And then are they going to be in the air, on the ground, in the borehole? The purpose of all this is to show you that, like, wait a minute, there's a lot of routes down this path, even if you decide to use them. There's a number of decisions that have to be made. And so understanding the fundamentals in this is going to help a lot in making that decision. So of these three problems, one thing that's interesting is electrical conductivity is diagnostic for all three. So whether it's minerals, or water, or ordnance, the electrical conductivity is an important problem. So we're going to concentrate today almost exclusively on electrical conductivity. So with that, I'm going to look at the oldest experiment. Yeah, I might be. How many people have actually acquired DC resistivity data? About half.
That's quite a few.
That's quite a few. Well, yeah, but we got GRS here, right? So just a whole row. Okay, DC resistivity. Perhaps one of the oldest geophysical experiments, and certainly one of the most robust and really useful ways of obtaining some information about the subsurface. So here we are at a source, input some energy. Now our property is resistivity or reciprocal conductivity. What's our motivation? Well, maybe it's minerals, maybe it's water in mine, oil, gas, water, geotechnical work, just a whole host of potential applications. It's worthwhile, I showed you this earlier, it's the image of electrical conductivity of various kinds of rocks. And it varies over many orders of magnitude. It's also very complicated. I mean, if you look at a particular, if a rock has a resistivity of 100 ohm meters, there's a lot of factors that kind of give rise to that. So here is, first of all, depends on the rock type. So what we're looking at here is a penny, and this is just for scale. And you see, first of all, there's a couple of different kinds of textures that are going through here. Got this versus this versus that. This looks porous, so there's a whole bunch of holes in here. Could be connected with a fluid. That fluid could be a conducting fluid. You have something like salt, or it could be really fresh water. Then there might be metallic particles in here. All of those would contribute to the ease at which electrical current could pass through, and so hence all contribute to the electrical resistivity. So it's complicated. What I want to do is to take you through the basics of the experiment, and I'm going to concentrate on something that is often not concentrated on, at least not as much as I think it should be, and that is just understanding the DC resistivity experiment in terms of electrical charges. That'll help us a lot when we think about survey design. It's also going to help us a lot when we think about the full time domain EM. And we've got a couple of case histories. So here's the basic experiment. We got an ore body. In fact, this one is from the Allura deposit quite a long time ago. And what have we got? Geologically, we've got an overburden that's fairly conductive, 12 ohm meters. I've got a host rock that's a couple hundred ohm meters. We've got a mineralized zone in here, which is has a very low resistivity. And on top of it, we've got a kind of a cap, a gossamer of some sort that's really, really resistant. So we'd like to find that guy. So here's our setup. We're going to have a generator and put two probes into the ground. So there's a current here, say plus current, minus. And when those currents go in, they pass preferentially through conductive material, and they kind of get distorted around the resistors. In doing that, they actually set up a series of charges on the outside of this, and those charges then give rise to electric fields and electric potentials that can be measured at the surface. So that's the basic experiment for the DC resistivity. We've got currents flowing in, charges being built up, and measuring that. So how do we obtain the resistivity from that experiment? Well, let's go back and look at Maxwell's equations. Now we're in steady state. So that means nothing is changing as a function of time. So the equation is reduced to something like this. We can show that the electric field is just the gradient of potential. And we have Ohm's law. We put it all together, and we get this equation here, which is really iconic in a whole variety of circumstances. This is the basis for DC resistivity, basis for ground fluid flow, groundwater hydrology, worked in medical equipment. So it's a huge thing. And we can actually solve this under particular cases. If I had a homogeneous Earth, and if I put a current in here, I can show that there is an exact solution, an analytic solution that looks like this. So I put a current in here. I'm at a distance r away from here. This has got electrical conductivity, and my voltage that I'd measure here is given by that, or this particular equation. So because there's this unique solution in this case, I can actually make a, I'm going to be able to actually get the resistivity of the Earth. So here's how it works. So let's suppose I put a current in the Earth. Now, where are the currents going? Well, everything's homogeneous, so they're going to spread out like this. And the voltage that I'm going to measure, or that exists, looks like this. Okay? So it's infinite right here, but it falls away. I take that expression that I have and I manipulate it. So I just put rho on this side. And what this tells us is that if I know the voltage at any particular location, and it doesn't matter which location I have, and I plug it into this formula, I'm going to get out a resistivity, in this case of 500 ohm meters, which is what the resistivity that happens was. So that's a way that, like, just by measuring a single number, we could actually obtain the resistivity of the Earth, which is, I think, is kind of cool. Right? Just measure a number, and you've got some information about the Earth. Well, in fact, we can't do exactly that experiment because we always have to have grounded transmitter. So I need to put a current in here and draw a current out here. So I've got a loop. And then I also am going to need to measure a potential difference. So I'm going to have two probes for that. I'm going to be consistent throughout this whole course that the A electrode is always the positive, the B is the negative, and it's positive. So we can use this particular configuration and the fact that we knew how to solve things just for a homogeneous Earth, and just use various combinations of distances here, add everything together, and I end up with a solution that says that the potential difference that I measure here is going to be the resistivity of the Earth times this sort of geometric factor. So we know those because we know where we can put them. So if I look to see what happens, so I put an A electrode here to B. So now my potentials are looking like this. And my currents do exactly what you think, right? They go out here, they're going into here. So I've now changed them considerably. I take 2 points, doesn't matter which ones, plug them into this formula and rearrange. I get that the resistivity is given by whatever that is, measurement, divided by this. And in this case here, it's also 500. Okay, so that's the basic experiment. It's always going to be 4 probes, 2 for currents, 2 for potentials, and there's going to be some geometric factors that's going to be used, and that'll allow us to give it the resistivity. Okay, so now the first question is, okay, suppose we take this, and now we decide, let's put on a a conductive, a less resistive layer on top. Okay. So what's going to happen? What's going to happen to this? How are these currents going to change if I put something that's less resistive up here? Anybody? What's going to happen to the currents? Are they going to stay the same? Are they going to get affected by this layer up here? Anybody? Libby? Somebody's back.
It's going to be compressed into the layer.
Going to be compressed into the layer. It's one way of putting it. They're actually, the currents are going to be preferentially in there because this is a low resistivity path. So the currents will try to travel through those regions of low resistivity, high conductivity, and get there. So now the most of the currents are in here and some are down here. So what happens if we took that formula that we had before and we applied it? Now we still take two numbers here, and now we get a potential difference applied in, and we get an apparent resistivity of 226. Okay, so this is 100, that's 500. We get an apparent resistivity of 226. Seem reasonable? Unreasonable? It should seem reasonable to you because in just a homogeneous half space for 500 ohm meters, we obtained the 500. If we just had 100, we obtained 100. Now we've got some currents in here, some currents in there. So, we're kind of getting sort of an average value. So at this particular point here, where our apparent resistivity is truly that, it's an apparent resistivity, and it's telling you something about maybe an average. So we have an app that allows you to explore with that. So you can put the current potential electrodes anywhere, and you can change the resistivities of the layer thickness. And you can make that relationship between where the currents are going and this apparent resistivity. So there's often names that are given to particular geometries of electrodes. So here's one, it's called a Wenner array. It's a 4-electrode array, but these guys are all equispaced. And there's something called a Schlumberger array. It's basically the same, except that instead of measuring over equal spaces, you just tend to have a small separation for your potential electrodes. But those two things are very similar. The thing that I want to mention here is that a critical element here is actually the size or the length of this array. So any array will have a particular scale length attached to it. And depending on the size of the array and what we do with the sounding is progressively make the array bigger and bigger. And the idea there is that you'll see deeper, and we're going to get an apparent resistivity curve out that maybe looks like this. So that's apparent resistivity as a function of the array length. So let's just take a look at that a little bit more. So here's a case where I've got current electrodes that are sitting really close together. So here's my earth. It's still 100 ohm meters, 500. So I've got currents that are sitting pretty close here. The current's kind of just sort of going in that top layer. And the result of that is my apparent resistivity is just a touch over 100 ohm meters and would plot on this particular scale. If I extend the length of that array, make the currents out here, now we see I've got more currents coming in here. My apparent resistivity has increased to 135. If I extended more, my apparent resistivity is going up to about 240. So even though, see, at this time, my separation between my current electrodes is 60 meters, and this thing is only 8 meters thick, I'm still heavily affected by this near surface layer, and I haven't even got up to the final asymptote of 500 millimeters. So there's a kind of a summary here for something that's called sounding. In a sounding, let's suppose I'm thinking that, okay, the Earth is just one dimension, and I'm just going to start small and gradually get bigger and bigger and bigger. And the larger I get, the deeper the currents go, and the more I'm going to see what's at stake. Okay. So that's the principle of a sounding curve. And an important aspect here is that the scale length of the array actually has to be larger than the depth of the target that you're going to see. And a good rule of thumb is about a factor of 3. So this is a plot of the data. That's apparent resistivity, and that's something to do with the geometry. It's just a data plot. It does not tell you what the resistivity is at any particular depth. To do that, we've got to invert the data. So, and what we mean by that is we're going to start with our measurements, and then we're going to go through a box here, which is an inversion program, to recover something that has got true depth and resistivity, and that would be the thing that you would then interpret. Now, I spent almost my whole life working on this box in various things, but we're not actually going to talk about that today. So we're going to assume, excuse me, that the inverse problem can be solved. All of the problems I'm going to show you today are going to be solved in almost exactly the same way, where we take the Earth, we divide it up into a whole bunch of cells. So in 1D, those would just be layers. In 2D, they'd be infinite cylinders. And in 3D, they're just volumetric cubes. We get a whole bunch of these, probably far more than we have data. And then we're going to manipulate the values of those so that we reproduce the data and satisfy other geologic criteria. So that's, excuse me, that's the goal, and we want to go ahead and do that. And in this particular case, what we ended up, so this was the true resistivity, and we ended up with some kind of curve that. Lindsay, could you see if they can get some water? So let's go back here to this business of the charge. So I said the current is going through here, and it's going to generate a charge on this side. So let's just think about where that comes from. So we're in steady state. That means that there's nothing that is that's changing. So there's nothing that's changing. That means there's a current that's coming through here, and it's as big on this side as it is on the other. So J1 in unit 1 is the same as J in unit 2. Okay? But the current density J is the product, as Ohm's law, sigma times E. So that means that this quantity is the same on both sides, but if sigma 1 is different from sigma 2, then that means E1 is different from E2. Okay. How can I, at a boundary, introduce a discontinuity in an electric field? Okay, so first year physics, for those who remember, the only way that you can do that is that you have to put a charge there. So in other words, if I build a charge on a boundary, then the electric field is going to go outwards with a positive charge. And so the electric field as I'm measuring across is going to change discontinuously here. Okay. So here's the basic principle. I'm going to drive steady state currents through something. That means there's going to be a charge buildup. Each charge is going to give rise to an electric field via Coulomb's law, and I could go ahead and measure it. So here is the principle of the DC experiment. So let's just see how that works. So I'm now going to put in a uniform background medium, but I'm going to put in a conductor in here. So there's going to be a conductive cylinder. I'm going to put a current in here. And now you can imagine what happens, right? This is intuitive. Your current going in is a conductor, it kind of gets sucked in through a conductor, and then it comes back up here. Good. So what's actually happening? Because there's like this sort of change in direction here, and there must be a charge buildup that is occurring on here, and we can evaluate that charge, and you can see that there's a negative charge on this side where you're going from resistive to a conductive medium, and a positive charge on this side. So this is what the charges actually are going to look like, and they're going to give rise to a secondary potential that looks like this, and we're actually going to try to measure that, and that's going to be the information that we have about here. If you want, sometimes it's also really interesting to look at the currents in this case, because we initially had primary currents without this thing. You remember how they work. And if we look at the difference between the total currents and those primary currents, we'd end up with these as secondary currents. So these charges there are associated with these secondary currents that they kind of look like a dipole. So you can kind of see that. Let's look a bit more closely. Let's suppose we've got a system like this. We're going to fix our current electrodes at two positions, and we've got a 1 ohm meter cylinder and a 500 ohm meter background. If I take my voltage probes and put them right here, I'm actually going to measure reduced voltage, and if I put in my parent resistivity, I see that I've got 430 ohm meters. That's good, right? So I've got a conductor here. I got 500 ohm meters, and I measure something over here, and I've got a lower resistivity than this background. So that's saying, hey guys, maybe there's a conductor out here. So that looks good. Now if I change, and if I put my potential electrodes out here, they're actually, it's coming back to the background 500, about 500. But interestingly enough, it's actually larger than 500. Not very much larger here, but it's larger. And so that should raise an interesting question for you, like, wait a minute, what's going on here? Because there's nothing in here that's larger than 500 ohm meters. I got 500 for the background, and that's less, and yet I'm actually getting a number that's larger than anything. Think about that, but we're going to come back to that because there's some interesting things that are going on here. So as I'm moving along through here, I'd get apparent resistivity of 500, a little bit more, 430, and 500 again. So it'd be a little bit of a dip. Because we've got things that are laterally changing, so instead of a sounding curve, because we don't really know where the object is, we want to somehow do a profiling. So that means that we need to move our system laterally. Imagine now what happens. Let's suppose we take this kind of a system. So here's our current, here's potential. And now because it's all very small, you're moving, the currents are just kind of lining up here. You're not seeing very deep. And if I plotted my apparent resistivity as I did a profile over here, I'd end up with just basically 500 ohm meters. Okay, so I'm just seeing back. If, however, I make the array bigger, so now I make something like that, now my apparent resistivity profile looks like this. So now it's actually really sensitive. You can see it's 300 ohm meters right directly above that sphere. Notice also that overshoot that I was talking about, it's now pretty significant. That's sort of like 520 ohms. Again, we'll come back to that. So in summary, we've got soundings, right, which means that you're not thinking about things in 1D, and you're just going to make things bigger and gradually see deeper. And then you got profiling, which means that you want to take your system and move it over. So with each, I mean, you can think about each size of array as really kind of sensing a particular depth. And so if there's somebody at the back that I really want to discover, I just have to make this thing very large, and then to try to find where he is horizontally, you need to kind of translate it. So there's a whole host of things that you can do. They come by different names. This one's called a gradient array, and basically in here we're just going to put the current electrodes out at some large distance, and we're just going to measure the potentials in a whole bunch of different areas here. And the others are all based on the fact you've got a 4-pole system, but if you're using everything, you can call this a dipole. So here's your current dipole, here's potential dipole. But if you take one of these currents and you just run it off a long way, a couple of kilometers off to the side, and you basically end up with something like looks like this. So it's like a pole dipole. Or you could have the potential electrode going out. So now you could have a pole survey. So those are all things that you'll see, and contractors will talk about gradient arrays, dipole, pole dipole. Those will be common expressions, and that's basically how you get them. So we have to plot the data. In the cases where you've got just 2D geometry, the sort of the accepted way is like this. We have a current electrode, we have a potential electrode, and we just drop 2 lines at 45 degrees, and they're going to intersect at some point. And we're going to say on this piece of paper or plotting plane, I'm just going to plot the apparent resistivity there, and it's being obtained by that same formula that we used before. If I move this, that plots at a slightly deeper level. Move it again, plots out here. So there's going to be a plotting plane on which this axis is kind of like some pseudo depth. You're thinking about looking deeper as you go down here. Oops. So what I'm going to do here is to show just a little cartoon about how the pseudo-section is generated. So here's our dipole-dipole system. And in this configuration, plots here. If I move this out, it's going to plot down here. Move this out, plots down there. So that'll complete that row of numbers. And then we're going to move everything over, do the same, dot, 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 dot. You can see we're just gradually plotting up the numbers. And then we can contour. Okay, that is called often a pseudo section. Pseudo because it's not really a reflection of the Earth. So this is true horizontal distance. This is some kind of pseudo depth. Sometimes that'll be denoted as an n number, 1, 2, 3, 4. N just tells you about how far these electrodes are apart. What I want to stress here, and this is extremely important, although the take-home message is becoming more prevalent these days, is that this is a map of the data. It is not a map of geology. Okay. Here's an example. Like if you just had a single block buried in a half space, then the pseudo section might look something like that. So that doesn't look like that, except that, under certain conditions, you might think like, oh, maybe I could drill in here and get the block. And under those conditions, you might be right. But it doesn't take very much to screw things up. I put a few conductors in here. Okay. So these are just little conductive blocks. I still have this guy. I look at the pseudo-section, and now it looks like this. So this is really mocked, right? You can't see anything. You can't do anything with that. And here's another one that has two conductors in it. And this is a valley, so it's got a bit of topography. And if you look at the pseudo-section, you get like this. Sometimes people get really excited about seeing red blobs on a map, and they think, oh my God, I got to drill that, right? Give me that drill tomorrow. Okay, so then they drill right through here, which puts them right through there, right? And then they say geophysics doesn't work because it wasn't there. So you got to invert the data. So here was our pseudo section, and now we take it, and we do the same inversion process, except now this is in 2D. So here's our example. If we took the resistivity model, here's our pseudo section. We do the inversion, and here's the result. So it's actually pretty good. We've got something that's localized on the place it should be. It's smooth as you go through the outside. But that's because within the inversion process, we're regularizing things in a particular way, and we're asking for a smooth model. So that character comes from the inversion algorithm. But that's a great result, right? No problem there. Here's our model that's got a lot of noise, geologic noise, and here's the inversion. So again, we see the target body. But actually, interestingly enough, we also see some of these other distortion things. I mean, maybe they're interesting. I don't know. But if we're interested in the target, we've definitely seen that. And in this GIF model, which looked like this, we recover. But we don't see down to the bottom of that. But we had an electrode ray that was at the surface. There simply wasn't enough penetration depth in that in that survey to be able to see them. But you've got that near surface stuff, and again it's sort of smoothed out a little bit because of the algorithm. Okay, so that's kind of like 1D, that's 2D. But the world is 3D. Okay, and now things get seriously more complicated. And you've got to worry about a lot of things. You've got your target, okay? What's its shape, size, depth? And what about the background? I mean, like the host could be really, really rough, all kinds of different background materials. It could have a lot of topography. And then if you do have an ore body that's buried in there, now you got a lot of questions, right? Like, okay, where do I put the currents? Should I use a 2D acquisition, 3D acquisition? That's just for the sources. Now, what about the measurements, right? Where do they go? Which measurements? What are the effects of topography? Lots of questions, and they're serious questions, and you have to address these questions. You can't. There's no free lunch here. You have to really look at these things and address them. But the one thing is that in all of this, the crucial element is sensitivity. So if I were to ask somebody for a definition of sensitivity, who would say something?
How much information can the data provide for a single cell conversion?
Yeah, okay, so good, yeah, so a parameter in the model, whether it's the conductivity of the cell, here. So if I've got something that, maybe I'm looking for something like this, right? And I decide somehow I'm going to try to put a current electrode across here, and I'm going to measure this potential, okay? So the question then is, if I change a parameter in here, so it could be the value at a single pixel, or it could be a whole could be value of this whole object, or it could be a boundary value, doesn't matter, whatever those parameters are. I'm going to change that a little bit, and then I'm going to look at the result and change in the data, and then get the sensitivity. Most times when people look at sensitivities, they kind of put it all into one kind of hopper and just calculate out the kind of like the global sensitivity. I think it's actually more fruitful to just take it a bit slower and do two things in understanding sensitivity as it relates to survey design. And that is, the first is you need to excite the target, and then you need to measure something. So they're actually two different things, and it's worthwhile separating them out as you're thinking about any particular experiment or survey. So let's think about first about exciting the target. Okay? So we're going to put our sphere in here, and here's our charges that are built up, or if you like, secondary currents. And that's good. We're exciting this target. There's significant charges on there, and yeah, that's giving rise to measured potential or secondary potentials. Okay, so that's good. Where should we take the measurements? Well, once you understand this, and you're going to be measuring a voltage difference, I mean, you'd clearly like to have one end of your voltage probe the closest possible to this guy. If you're confined to a surface, then you just want to be as close as possible to these charges, and at the same time not have both ends of your potential measuring device be too close together, because you're going to need to get a significant difference. But that kind of intuitively sort of sets the idea about the excitation, and now how you would want to measure it. The other thing that is important is coupling. So suppose we had a thin plate, and now we've got a plate. I mean, the plate could be in this direction, or it could be horizontal in that direction. So what are going to happen to the to the currents? The currents in one case are kind of go in like this. You can see it is a conductor. They're kind of sucking in. If it's horizontally, it's going to look like that. So that's certainly going to change that distribution of charges on here, which is going to affect what your data are. So coupling is important, geometry, how everything is working. And then the next thing is, okay, what if you have a resistive target versus a conductive target? So first of all, would you expect to see any difference? It's going to make any difference? So let's suppose I have a target that's 10 times more conductive in the background and one that's 10 times more resistive. Am I going to see the same kind of excitation response? Equally easy to see the resistor or the conductor? Anybody care?
You can have different response to the current between the conductive and resistive materials. It's going to resistive materials are going to go away from the material, and conductive are going to pass through.
Perfect. Exactly. So if I have a conductive target here, currents are going to kind of get sucked in, and there are going to be some charges built up on the outside of that body. If I have a resistive target, now the currents get deflected, they go around, and it turns out that the charge buildup on that body is actually a lot more. So the currents change, the strength of the charges change, and also notice that even importantly, the sign of the charges change, right? So if I'm going from a resistor to a conductor, which I am here, I get negative charges in this side, positive in that. If I reverse that, I'm now going to get positive charges on this side. So I'm now going from a conductor to a resistor. I get positive charges on this side, negative. Okay, so there's a lot of things happening, and the strength of your resultant fields and signal are going to depend upon, you know, whether it's a resistor or a conductor, as well as all of the orientation. So to summarize that, summarizing sensitivity, we got to excite the target. That means we need to drive currents in, we need to get good coupling. And then for measuring the data, we somehow want to get in good proximity, as close as possible to the target, and be concerned about the, you know, electrode orientations and separation. And the other thing is that background is important. Okay, so now come down to some survey design questions. And here again, always it's important to be clear on what your objective is. And your objective might change at various times in a particular exploration survey too. But if your objective is just to find a layered Earth, then do a sounding. If you've got a target body that's 2D and you know the geology, then you go perpendicular to that geology and you just do that, that 2D. If it's a 3D body, you need 3D coverage. So you need to be exciting that body from multiple directions, and you need to be recording multiple responses. Important thing is also what's that background conductivity, and what are the noise sources? Are there power lines, fences, things like that. So it's really hard to be very. I mean, there is no way to give anybody a single black brush recipe that works. You really just have to come down to basics. And in a case like this, let's suppose you're trying to find a target at some depth, and you're hypothesizing, okay, well maybe I could put current here and potential measurements here. Does that seem like that's going to work or not? Well, you've got to go through these following steps. First of all, you define your geologic model, and then you've got to assign physical properties. So that's sometimes not an easy task, but you might have to work a little bit to do that. But you've got to kind of figure out what your host is, and you select a survey, and then you simulate. You do 2 forward modelings, one with the target and one without. That's it. You with the target, without. And without the target, maybe you get this blue line up here. And with the target, you get the red. And then you look at the difference between those 2 points. So that difference, which is your measured minus what your primary was, that has to satisfy generally a number of at least 2 things. One is its number has to be large. It has to be greater than some floor value, which is connected with the general ambient background noise. And in most cases, although not all, but in most cases, you also want that number to be large compared to its primary by at least a few percent. And you're doing BC resistivity surveys, for instance, very often because you don't know exactly the geometries of the electrodes and various other things. Assuming your data are about 5% correct or a couple % correct is often a pretty reasonable thing. So assigning a percentage plus a floor is good. And you can kind of take that into account as you're thinking about, okay, is that a particularly good data to collect or not? What I want to do now is to go through a short case history. And Terry is well acquainted with this guy. We took it's Mount Isa. So this is a prospect in northern Australia, and I'm going to parse it out into a 7-step performance here, where we go through our sequence. First of all, here's the geologic setup. I don't think it's particularly important to know the details about each of these guys, but there's some important units in here. First of all, there's these siltstones in blue, which can house mineralization. There's some volcanics out here, and there's also this red thing in here is a black shale or a breakaway shale that turns out to be important. And really the idea is that can we somehow find a mineralized zone? And that mineralized zone is going to be a conductive unit buried in these siltstones. So we're going to look at each of those units and establish what their electrical conductivity is. So these siltstones have kind of got a moderate conductivity. The volcanics that we've got are very low conductivity. The guy that we're looking for, it's called a Mount Nova horizon, has a high conductivity, but he's not the biggest kid on the block. There's a breakaway shale here that has a very high conductivity. What we're going to be doing in the VC resistivity is looking for something that is pretty high with respect to its background, but may not be the highest conductivity that we see. So it's a little bit of a challenge. What are the data that are going to be collected? The geology is kind of linear, and so we looked at basically acquiring 2D lines, so there's 10 2D lines. And in this case, they plotted with a pole dipole, so we talked about that. So the current source is at the end. So overlay this whole region with electrodes, and then you populate, put a current here, measure the potentials, that gives you this. Then you move the current over, measure the potentials, dot, 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 and then you gradually end up with this triangle. That's your pseudo-section. So here you have 10 pseudo-sections. The red is conductive, so there's something conductive here. Blue is resistive. So that's 10 pictures of your data. We talked about excitation. If I've always got the current on one side, things are going to be excited preferentially in one way. So if I excited things differently, I could do that by using this other current electrode, running this one out to infinity this way and populating back here. So that gives me now a different excitation. And you can see the data maps have changed, and now I've got some big conductivities over here. Okay, so there I got 20 maps of data. There's only one Earth model out there. So can I somehow work with these and get a single geologic model? So what we can do is the following: formulate it up as an inverse problem. And yeah, that's really, the result I'm going to show you is it was actually done quite a few years ago, and I'm quite proud to say that I think this was one of the first 3D DC IP inversions that were done for the mineral industry. And the case history has withstood the test of time. It's still great, and we've written it up in EM GeoSci. The Earth model is just a volume, and it's got about 500,000 cells or something like that in it. And those are going to now be manipulated to recover a 3D representation of the geology that is in this block here. And what I'm going to do, I'm just going to slice this through from front to back, and then from top to bottom in plan view, and then I'm going to spin it around and change the isosurface value, so at the end we're seeing only the most conductive units. See this big red on the right? Now we're just changing that isosurface value. In the end, it looks like this. So this is great. I mean, from the point of view of going from geophysics to geology, this has done a great job. There's this huge conductor in here that turns out to be shale, and then there's a couple of other guys here. If we plot it up in a color section, it looks a little bit better. Looks like that. So our understanding of what's going on is as follows, that this unit that's coming in here is that black shale unit. So that's great to delineate. It's totally uninteresting from an economic perspective. There was, go back here, there is a moderate conductor coming in here that's kind of sitting out. So the dark blues here are volcanics. These guys here are probably siltstones, and this moderate conductivity that's coming in here could be a reflection of that Mount Nova horizon. But it's not, that is certainly not a slam dunk at this position. However, the real information for the existence and the location of the mineralization is coming not from conductivity, but will actually come from the IP part, the induced polarization part. So this is as far as we're going to take this case history at this point, but at the end of this, well, sometime tomorrow morning, when we finish up things, we're going to come back to this case history and look to see what's happened. There is another case history we will not go through, but for people who are interested in dams and integrity of dams and trying to understand how they're, this is something around, as we've been going around the world, has really captured people's imagination. So what you're looking at here is a dam. There's water on this side, and you know, there's just sand on here. It's a dam in France, and what it's leaking. And what they're trying to do is to try to find out not only where the leaks are, but actually try to go full circle and try to find out, okay, how many liters per second are actually traveling through here. The procedure is to go through and measure the self-potential. So self-potential occurs when you've got fluid that's flowing through a porous medium. And effectively, you end up with a charge buildup at one end of a cavity and an opposite charge at another. And so you just go ahead and you measure the electric potential just at the surface of the Earth without any active source. So effectively, this is the active source. So measuring just what's called the self-potential and inverting that gives rise to information about how the fluids might be flowing. So that's a case history that we will not go through. What is there? I want to just finish before coffee and talk about one important thing, and that's the effect of the background resistivity. What's the background host? So remember here, we had this conductor in here in a 500 ohmmeter background. And yeah, we measured the potentials up at the surface, and we found a low resistivity here. So that all looked good. But what happens? What's going to happen? Suppose I take this image and I put in a resistive layer. So just a thin resistive layer above that of this guy. So what's going to happen? Anybody?
Regulating the interface.
Okay, and what about the currents? Are we? Is it going to affect our ability to see this guy? going to matter. Oh, somebody. Or we can ask our GRS team here. Anybody? What's good? I put a resistor up there. What's going to happen?
Hard to make.
Yes, if I.
Yeah. So it's going to be really hard to get the current in, right? So what we're going to see here is that if we put this resistor in here, I can't drive the current down through there. So the current all stays up in here. And there's nothing really that's coming in. It's a little bit of an optical illusion that there's still stuff there because it's just the way we had to plot it. But now the apparent resistivity is 1600. So instead of being 400, it's now 1600. And that 1600 is purely the consequence of this resistive layer. And we know that. So this next one, I gotta redo this modeling, but without the sphere there. And I get a apparent resistivity of 1600. So this is really important. So I go ahead, I think like, okay, I set up my DC resistivity experiment, and I can see this object looks great, but then somehow, some way, there's a thin resistor that's just over you, and it doesn't have. I mean, it could be infinitesimally thin. Like just imagine, big crack of air or something like that, or just some layer of really high resistivity. That's enough. It just completely you've shielded your target and you're hooped. Okay, resistive layer, you're hooped. How about a conductive layer? Anybody? Chileans are really quiet. I don't know, that's amazing. You guys got to drink more pisco or something. Let's just say liven this up a bit. Okay, I put a conductive layer in. What's going on? What's happening?
Well, currents going through the conductive layer.
The currents are going to go through the conductive layer, right? So now I put a conductive layer. Now they're not even flowing up top. They just see, okay, I'm short-circuiting, right? So here goes the current up here. And if I look at now my apparent resistivity, I got 47 ohm meters. And if I do it the same without that thing, it's 47 ohm meters. So that's the bottom line. So that was what I tried to do there is start like right from basic square principles for the DC resistivity. We went through, talked about the charges and how everything's flowing, and show the inversions and how incredibly successful DC resistivity can be. At the same time, there are cases where you are limited, and that is actually the segue into electromagnetic induction, because now instead of trying to drive current through, we're going to induce currents in the earth. So that's where we're going to pick it up right after coffee with, first of all, the basics, and then look at some inductive sources both on the ground and in the air. Good. And I think coffee's there, so I think we're just right on time. We said 10:45? Yes, exactly. Nicely done. Yeah, exactly. We're right on time. How about that? Oh, that's perfect. Yeah, I saw you. I thought, wow, it worked. Like, I think to get it
working back, we need to build it into the project. But right now it's not.
Oh, okay. As long as I just undo a whole bunch of crop drops and get some water. Yeah, I mean, we can mess with it, but I don't know. But what's it, do we need it here? A little bit, but like, not much. But I mean, because you're so close anyways, it doesn't. Maybe, I think just like. We could put it one try, and if not, then we make it.
Nah, sí.
Pero sí, para el le gusta y pero no volvió a ser un
Mejor eso que no fumar nada.
Claro.
Eso es lo que quería hacer.
Estoy participando. Ah, ya.
Testing. Oh, excellent. That works then? Can you hear me a bit more?
Yeah.
Okay. Oh, perfect. Yeah, I did.
Oh, it is off.
Oh, is that ambient noise?
Yeah.
Okay. I'm going to buy a coffee.
And oh, yeah, one more thing. Do you want? So this is a list. Do you want that up there just so you can?
Oh yeah.
Take a name and-
Oh yeah.
It's called. Perfect.
Let's go see what we have. But actually, sorry, you're busy?
We are, yeah. Not so much last year.
That sounds. We're going to
We've got very close as we work on board. It's quite light.
Yes, that's good.
My parents are so bad at sweat. It's a great
Okay, that's first challenge. So, and how do you prepare your releases? Well, you're not going to tell them?
No. Two out of all part. One part of the 5 years, the gate fees, the smaller, larger, and the light. If you recall, the
Okay.
And just to add some sugar that we use like liquid sugar. It's it's one part. One part of it.
And you compare
in my opinion, if you use one instead of the brown, it's better than selling white, yeah. They add the color.
Just go the balls up by the carbon there. That's university. It's a lost great story goes, I think. No, died all over the world. It's not happening anymore. We had a go at it as well, right? I've had some really friends. That's very good. It is a nice one. Very good.
Way better. Yeah, you can provide in the supermarket.
Oh, yeah, whiskey sour.
No, I've never done it. You met in Brisbane. She said to you, why don't you come to Chile and get a course? And you said, well, you have to have a lot of friends who like you. And you probably get more people like that too. Oh, well, it is though. It's fine.
I can go from work, but certainly not.
I know. That's the consequences of
And then you want to party.
Well, what kind of music? Oh, like all the retro.
This is, you have
¿Qué vas a llegar en México? Que tenía, ahí me y así me pierdo, yo he entrado aquí 2 veces. Coming back, so taking down your day, coming up your day.
I don't think that it's one community of geophysics there yet. Yeah, so before it was only 1 day. So it's continuing to grow. Yeah, because if they end up having it's only 1 day, we will also like others responding the whole day.
If you're interested, it's not that far from the ship. Go to San Cristobal, it's too easy. You'll not find it the good thing is that you are close to the stars and very nice places. And you are pretty close to the place that you're staying.
I relocated to where I was
Regularly, but currently the codes that we are using for our version modeling are what based on force we are using scripts called yeah, so point our clients wanted to make a quick QC of the data that we provided them. So it was a little bit complicated for them because we provided a text file, so we import that file and make some nice yeah, but this was really good. End of the process, so we already get the evidence. Yeah, you can run a marker. It's regular errors for regressions. We run some logic, so we define the errors of data according to the feature of the logic. When I saw your website, I saw that you were working on Python. I am a reader. So yesterday night, I downloaded the Python code. So I like programming Yeah, I wish I could have these
Okay, guys.
Where are the blade to go next?
Does that pick up?
Do you want to show the apps now or?
No, I will do that. Maybe I can reconvene. Sure.
You might want to just double check that everybody is aware of this changes.
Okay, so for people at the back, I think maybe you can now hear me a bit better. That's perfect. So this is another practical application of Maxwell's equations, right? Because up until this point, we weren't able to get connected with our little speaker there, but now I'm speaking, electromagnetic waves going out, being picked up by the antenna. So all of those same equations, right? Exactly. So now we want to start looking at EM. And what's the motivation? Well, first of all, suppose you have large areas to be covered, maybe 100 kilometers squared. Here is a case that we just saw with resistor shielding. You can have places that are hard to inject. Chile in particular, with all that caliche, is a challenge. Rugged terrain, probably also in Chile. So these things kind of motivate looking at something a bit different, and we're going to do inductive source. I'm going to break it down again. My philosophy in teaching anything is that find the smallest little segment that you can, and do that, and then do another little segment and gradually build the little segments up, rather than putting things together. So we're actually going to spend a little bit of time looking at Ampere's and Faraday's laws. And I have a circuit model for EM induction. And we're going to look at frequency and time, and then especially currents in spheres or currents in anything, because currents turn out to be the diagnostic fingerprint of any EM survey. So what's our basic experiment? Well, we've got a transmitter and a receiver. Perhaps they're towed in a bird. They could be on the ground. This transmitter is putting out a primary, we call it the primary field in here. So it's putting out a field, we call it the primary field. And that field is going to be time varying. Oopsie. And that time varying field is going to generate an electric current everywhere. If there happens to be a conductor, then that will mean that there's going to be currents that are generated in that conductor. And then those currents are going to generate magnetic fields on their own, and they can be measured at the receiver. So that's basically the process. Time-varying magnetic field generates currents in conductors, and that generates magnetic fields that you can get everywhere else. So let's just kind of dig a bit slowly. Let's look a bit at the transmitter. Again, the transmitter could be operating in the time domain or the frequency domain. For Maxwell's equations, we're going to use them all, except we're going to get rid of one term here. This is the, D is the electric displacement, and we're going to get rid of that time variation. And that's going to give us what are called quasi-static Maxwell's equations. If we look at Ampere's law, it says that if we have J, then that gives rise to a curl of H. So this operator here, for people who are not familiar with a curl operator, basically you can think about it as being some kind of circulation. So if I have a current, then that gives me some kind of circular magnetic field. And I think you're all probably familiar with this with respect to a wire. So if I have a current in a wire, then you put your thumb in the direction of the current, and then your fingers sort of go around, and that gives you the direction of the magnetic field. And in this case, the magnetic field from a wire falls off as 1/r. If I take this wire and I wrap it in on itself so that I have a loop, then now I've got a magnetic field that kind of goes around like this. And if you looked at that magnetic field, you'd say, oh, it just looks like the field or like a little bar magnet, because you've all done that iron filings experiment. So that's really the field of a bar magnet. The mathematical formula for this is given by here. The important parts are that, first of all, that the field falls off as 1/r². That's important. R is the distance between the center of that loop and where you are here. And M is the sort of the strength of the field. It's the moment of the field. It's the magnetic moment. And in the case of this, it depends upon the product of the current and the area of the loop. So then we have Faraday's law. And that says, okay, so I've got a time-varying change of the magnetic field, and that's going to be related to an electric field, but again, it's that curl thing. It's sort of like a circular thing. So if there's a time-varying magnetic field coming on you, then, and if you're a conductor, there's going to be like a circular kind of current. There's a minus sign out here that's due to lens, and that helps us determine which way the current is going to go. And the currents are always going to go in a way so that they oppose any change in the magnetic flux coming through. And then we got Ohm's law. So here's how you get currents. You get, from Faraday's law, you get time-varying fields generate electric field. And then from Ohm's law, if there's ever a conductor then that gives rise to a current density. So perhaps you've seen this too, what we're looking at here. Here's a magnet, and this is a coil, and it's all kind of attached to a circuit, right? So one end of the coil comes up to here to measure the voltage. There's a light bulb that's connected with this, and if there's a current that ever goes through there, then that light bulb is going to light up. Up there. That was interesting. So, okay. So it's setting up like this. I missed it. What did you do? Oh, you turned it off. Oh, okay. Technology. So here's the here's the steady state operation. I've got a magnet that's sitting here. There's magnetic field lines that are coming through here, but everything is static. The important thing that we're going to determine is something called the magnetic flux. So that's the integral over the area of this coil of the normal component of B integrated through that. So it's given by this. So that's the magnetic flux. It's not the magnetic flux that's so much of interest, but the time rate of change of that. So the EMF, if we thought about a circuit with some kind of a voltage generator here, or something that induces an electromagnetic force, then we could get a current that's going through here. So what really is of interest is that the voltage is related to the time rate of change of this flux with that minus sign. So in this case, nothing's changing, so it's zero. And there's no current coming through there. If I take the magnet and push it in, so the magnetic field lines are actually stronger at the end of the magnet. So I'm now going to have a voltage that is actually negative. So I'm pushing it in here. There's going to be an EMF that's induced in here, and there's going to be a current in the circuit, and the light bulb is going to go up. If I do it in reverse, if I pull this thing back out, now I'm still going to have a time rate of change of flux, and with this minus sign, that puts the current through in the other direction. So when I'm pushing it in, the current is going one way through the loop. Pulling it out, the current's going the other way through the loop. So there's a couple of apps for that. There's one for the harmonic and one for the transient. And both of them kind of work on the following basis. There's a primary current, or primary field that's going to be generated by this quantity here. So we've got this is good, I like that. We can do that. But in Chile, yeah. I'm Caucasian, like my hipster crisis. Everything's kind of calcium. Right. Okay. So we've got a loop out here. It's got a primary current here, so the P indicates primary. So that's going to generate a primary magnetic field that's coming down like this, and that's going to be incident on a target loop here. That target is going to be represented by a resistance and a self-inductance. So that's what the apps do, and they allow you to move the loops around and do all kinds of really interesting things. So you see what's going on. So let's look to see what's going to happen in a couple of cases. So here's, this is going to be the two-loop system, and here's the equivalent circuit that we have for this. Our target is given by a resistance of self-inductance. And now we're going to take a primary current and it's on, and then we're just going to switch it on. And yeah, I was wondering, I've got a, do you guys have this hum? Can you hear that? That's just the projectors? Okay. I didn't notice that before. Anyway, so we've got a current that we turn. So the magnetic flux follows the current, so that looks exactly the same. But if you looked at the time variation of that, then the only place that there's a time variation is right at the time that you're switching off. And then that is going to generate a current in here. There's an EMF that's associated with that. And then those currents are just going to decay in time. So the moment that you change that magnetic flux through this coil, there's a current that's generated with some magnitude I sub s, and then it simply decays away with some constant tau, and that tau depends upon L upon R. So that's very simple, and yeah, you could measure any time after that shutoff and get some information about what the conductor is. The thing that is important here then is what is sort of the response function. In this case, it's just this exponential. If we plot the response function log and linear in time, we get these are straight lines. So that's just an exponential, so taking the log of that. Or if we plot it on a linear plot, then we just have these decaying exponentials. So that's transient. But now if we have a harmonic signal, what does that do? Well, if I have a harmonic signal that's going in here, then that primary field is always on. So it's not like in time domain where we shut the primary off. Here, this is always on. And so if I looked at the current in the primary, it follows this red curve here, right? So it has some sinusoidal representation. So the primary current is just cosine omega t. If my Mike. Sorry. Thanks for coming. Okay, so suppose I ask them what could possibly happen to this inner loop here. Well, it's going to have a current, and that current has got to vary sinusoidally with the same frequency. There's no, it has no alternative. So the only two things it can do is to have a change in its amplitude. So it'll have its own amplitude, and it might have a phase shift change here. So you notice that the green curve, its peak is shifted a little bit from the red. So that's interesting. So we could take this curve, here, the green one, and we could decompose it into two parts. One part would look exactly like the red, so it had the same kind of phase, and the other part would be something that was completely out of phase. So in other words, I've got this green curve. So if this is my primary, then there's a certain part of my secondary that's exactly in phase with that, right? And then there's also a part that's kind of out of phase. So you can see that. Now that means that the secondary field must look like that. It's got its own amplitude and phase shift. And then we can, by decomposing this, we could write this in this form where there's a cosine and a sine. And there's a term out here which tells how large this part is. And this part is called the in phase, or sometimes it's called the real part. This part out here, which is reflective of this amplitude, is the out of phase, the quadrature phase, or the imaginary phase. I think of all of the things that causes the greatest degree of miscommunication between EM people and others is these use of these terms. You just say, oh, here's the real part, here's the imaginary part, oh, here's the end phase, here's the quadrature. These terms all mean the same thing: out of phase, quadrature, imaginary. And for EM people, when you get used to it, you just use them interchangeably. You just kind of get used to it. Those words all mean the same thing. And for the in phase and the real, they also just mean the same thing. But they're really simple, right? Just the thing to do is remember this diagram, because this diagram really tells it all. I've got a primary, I got a secondary. It's phase shifted a little bit. I could take this, decompose it into something that looks exactly as that phase, and I could decompose it into something that was, completely out of phase. That's it. It's that simple. It should cause no confusion. And just remember that diagram. Okay, so what about this phase? The phase is actually given by this quantity here, and so you see the phase depends on the three values here: omega, the frequency, L, and R. And that number is called the induction number. So any combination of these three parameters gives the same value of induction number, is going to give you the same response. So we could actually plot how much of this and how much of this exists as we change the induction number, and that's what this is doing. So this is an iconic plot for electromagnetics. It's the response function for a frequency domain system. Here's your response, and here's your induction number. So it's varying by 6 orders of magnitude. The real part, so that's this guy right here, starts at very low induction number, is 0, and then gradually gets up to close to unity, and it's 6. The imaginary part starts like this, has a peak when induction number is 1, and yeah, looks like that. So that's the iconic response function. So the bottom line here, if we have a step off or a harmonic signal, both of them are dependent upon the same equations, and the only difference is that in one case you don't have a primary field, and in one case you do. And so here you just have a single real decay. Here you've got some things that kind of has to get partitioned into like an in phase and out of phase portion. So let's look at secondary magnetic fields. We've got Ampere's law. So any currents that are generated in that loop or target are going to generate magnetic fields. So what about the receiver and the data? Well, you've got a couple of options. You can just measure the magnetic field directly with flux gate magnetometers. Each one of them could be 3-component flux gate that you'd use. Or you could measure it with coils, in which case you're measuring the BDT. And again, each direction of a coil is going to give you a single value. What we're generally interested in is kind of the ratio of the secondary field to a primary field. And these would have, if you're measuring with a coil, the same as the voltage in the secondary voltage divided by the primary. An important aspect here, actually critical, is coupling. We talked a bit about before in DC resistivity, but here our coupling is going to be on how that magnetic flux is penetrating, or how much magnetic flux is going through a coil. So imagine you have a transmitter coil like this, so the magnetic field goes like that, it's like a dipole. So if you have a receiver coil, or if here's your target, then your maximum coupling is going to be when you're in this position. If your target's represented by a coil that's oriented this way, then the magnetic field lines cross the end, so there is no flux through that coil, and hence there wouldn't be any voltage that is going to be produced there. the whole idea about coupling comes about twice, right? Because one, you can imagine this is the transmitter and this is your target. But this could also be, the currents in your target and a receiver coil. So there's always two ways in which that coupling can occur. So now there's kind of a simple model here for EM induction that is really useful. So let's suppose that we've got a body trying to detect. So we've got a transmitter. And so that's going to give currents inside here, and those are going to be measured at a receiver. So we're going to take this, and we're going to just transfer it to sort of 3 ideal loops. So we've got a loop for a transmitter, a loop for a receiver, and our target body is just going to. But from the ideas of coupling, we have to get the energy from here down to here, and how that's oriented is going to be really important. And there's a quantity here called M, and M1, 2. This is the mutual coupling between loop 1 and loop 2. That's purely geometry. You can figure that out. Then there's a coupling between M2 and M3. Again, that's purely geometry. And a coupling between the primary and your receiver coil. So what I kind of like about all this is that the quantity that we're looking for is really the ratio of the secondary to the primary field. And with this, we can, here's a complicated expression. And the first time, if you looked at that, you're wondering, like, kind of what's going on. But actually, it makes just pure physical sense. I mean, you could actually write this down just by thinking physically about what the problem is. Because what's HS? Well, got to get the energy from here to here, so that's M1, 2. And then back from here to here, that's M2, 3. So that's this one and this one. And then the primary is just this mutual coupling here. So that's M1, 3. So all this stuff in here just takes care of all of that geometry. But then you remember, like, oh yeah, there was the target here. So there's going to be currents that are induced, and there was the response function for that. So that means that we need to add in the effect of the response function here, which is this guy. So this is just another way of writing what that response function. So that means that we can almost write this thing down just by thinking physically about what is happening and knowing that there's a response function for a target. I want to take you through just the following the following case here now. I'm sorry, so your name is? Ariel? Close. Okay, so you're going to be the target body. Okay? I'm going to try to find you, right? So, I'm going to do it the hard way. I'm going to do it with geophysics. It'd be easier just to look at you. But okay, so we're going to use a 2-loop system. So it's going to be a transmitter coil and a receiver coil. Okay, and I'm going to kind of move this way. Now, the transmitting coil is putting energy out into you, right? So there's magnetic flux that's going through. So that's going to cause currents in you. So you're going to have a circular current that's going inside you. And that's going to give rise to a magnetic field that comes up. So as long as the transmitter is on this side, so then my primary field is going through the loop. There's going to be a current in here that is going to be such as to oppose, the current direction is going to be like that, and so that's going to oppose. So the secondary field is like this, the primary field is like this. On this side, when we're both on this side of you, I'm going to get some kind of a positive response. The primary field, secondary field are pointing in the same direction. Okay? Now we're going to move over a little bit. Okay? And so that gives us this part of the curve. So it's small when we're a long ways away because nothing's happening. And then it reaches a maximum and then it goes to 0. Okay, good. Question is, why do we get 0? So I'm moving along and now I'm going to get a 0 point. Where's my coil? Pardon me? Anybody? I think a lot of people know the answer. Don't be shy. But if I can dance to music, you guys can answer this question. Okay, why do we get a 0? I mean, there's still currents in you.
I'm having coupling because
Right. So there's, I think you're right. So there's still currents in here, right? But those currents, have this. They give a magnetic field. It looks like this. So if this receiver is right over top there, there's no flux through that coil. So there's no voltage. So I get a 0. Okay. Okay. Now my transmitter is still on this side, but now my receiver is here. So where my primary field is still like this guy here was going up, and he's now going down. So it's opposite in sign, so I now say, oh, it's negative. And so now I got this guy here. Okay? But then I got another 0. Where's he coming from? So I'm moving along. So I got 1, 0. So that I've still got currents in you, okay? Because my transmitter's over here, right? But then there's no magnetic fields coming. So that was a 0. And now this is optimal. I've got transmitter here, receiver here, good to go. And now I come a little bit more, and I get a 0 crossing. Why is that?
The source is not exciting the target.
Right. So now if my transmitter is here, the fields are like this, so now I'm null coupled with the target. So now there's no currents in here. So the first 0 crossing is just because the flux that was there wasn't crossing the coil, so that's a coupling issue. The next one is that there is simply no currents in here. So now there's no fields. And if I come back on both sides, I'm going to put that. The point I wanted to make about this is that as you're walking through, let's say, with a 2-coil system, there's a lot of stuff here that is just geometry. The shape of this curve, that just has to do with geometry. That's coupling issues. Okay? Now let's look at the amplitudes. I've got reds and blacks here. And the red is the real part, the black is the imaginary. So in this case, they're both identical. So the real and imaginary parts are identical, and that's because we're at an induction number of 1. Suppose that I change the frequency. Let's suppose I lower the frequency. Then my induction number is now going to be less than 1. What's going to happen? What's going to happen to that set of curves?
The imaginary part will be larger.
The imaginary, so the idea is that if I go this way, now if I look here, the imaginary part is greater. Are the curves going to have the same shape or not? Who says the shape is going to be the same? Who says the shape is going to be different? There's only one person that's thinking or that is willing to put their hand up. Shapes are the same. That's geometry. That's couplings, right? The difference, however, is that the imaginary part is now larger than the real. And similarly, if I go the other way, then the real is going to be larger than the imaginary. This is a really simple case, but there's a lot of stuff that's going on in here. And you should kind of work things out for yourself. Is if you change the field, which way the currents are going to flow so that they oppose that change, which way is the direction. You can sketch it out, and if you can actually get to the point you can draw those curves, then you really know something about what's going on. Okay, so what did we learn? Well, we've got some basics of EM induction, response functions of time, frequency, mutual coupling, and kind of have an idea for the data for frequency and time domain system. We also have a circuit model here, and the question is, okay, is that thing, of any use, or does it, is it applicable to geologic targets even at a crude level? So we can test that. How do we do that? Well, we need to do numerical modeling. So here's a coil, and here's our response function. If we now take this sphere, so now this sphere is 30 meters in radius. It's 2 Siemens per meter, buried in a resistive background. And here's a transmitter that's sitting right above there. And now I can numerically model this, and I get out response curves that look like that. So they're really remarkably the same as this guy. Okay, so that means that at some level, the ideas that you're getting with just a circuit model, coil model, that'll get you a fair ways. How did that code or those numbers develop? It was based on a finite volume technique in cylindrical coordinates built in SimPeg. So Lindsay is a prime author for that. There's been a few other contributors. This is a code that's open source, so you can get it from here. Actually, it's a tremendously valuable code. You'd be amazed at what you can do with it. So you look at this thing, for instance, modeling a sphere in a half space. And if you think about, as long as I can make everything axially symmetric, so I've got a transmitter that's sitting above here, and now I've got, everything is axially symmetric, means you could actually compute all the fields that you need to know. And also you can compute not only the fields, but also the the currents and charges that are built up, as well as being able to vary it for various kinds of things. Another aspect, and this is particularly important these days for the hydrocarbon companies, is that they're trying to make use of the infrastructure in existing hydrocarbon areas that they've been working on, because there's a lot of wells, right? So if you have a vertical well, and if it's both conductive and magnetically permeable, you can model responses with a code like this. Anyway, it's very valuable, and it's available. Okay, so we're kind of making some progress. The thing that we haven't yet accounted for has actually been propagation of the energy inside the Earth. We need to get energy from our transmitter to our target body, and then we got to get it back from the target body to the receiver. So that means that we need to address this question: how do EM fields and fluxes behave in a conductive background? So let's revisit Maxwell's equations. First order equations look like this. We can combine these into a second order equation that looks like this. It's got two terms. One is this term here, which we've actually concentrated on at this point. It's the diffusion term. And this is a wave propagation term. This is where the GPR kind of kicks in. We can take that equation and write it in this form. So it's called a vector Helmholtz equation. And the quantity that is of interest is this k. That's a wave number. It's got this expression. When we do our quasi-static approximation, we're basically saying this guy here is much less than this. And so K is just going to be the square root of this, which comes out to be like that. That quasi-static approximation is what we're generally going to be needing for most of the work that we do. So we've got this expression. So how do now we make use of that? So we need a plane wave. So what's a plane wave? A plane wave, you can imagine a wave that is sort of propagating down, and if there's nothing happening or nothing changing laterally, let's say in the x or y direction on that wave, we say it's a plane wave. So we can make one. So imagine a big current sheet that's going along the roof like this, right? So the current's going along this roof. So the electric field is clearly in that. That's x. That's in the x direction. And then the magnetic field, right-hand rule, says that the magnetic field must be like this. So I got electric field this way, magnetic field this way, and then everything just kind of propagates down. So that's what we're seeing here. We've got a current sheet. Here's the electric field, magnetic field, and everything propagates down. The expression that tells us about how that propagation is going is given by this. So it's got some amplitude at the surface. And then it's got this term here that's basically like the wave propagation term. And then it's got this term, which is an attenuation term. So e to the minus alpha z, alpha given by this guy. If we look at that term and we plot it as a function of depth, so if we look at how this field is going to decay down in the earth, it follows this kind of a line. It's sort of an exponentially decreasing line. And there's a special point where the field is decayed to 1 upon e of its value. So essentially alpha is equal to 1. And that is denoted by delta. It's called the skin depth, so it's a very important quantity for electromagnetic induction, as given by this equation here. Okay, so skin depth is the depth to which a plane wave decays to 1 upon e of its value. And that's going to depend upon the frequency and depend on the conductivity. So what happens in the time domain? So in the time domain, we've got equations that look like this. And for a quasi-static regime, it's got an equation that looks like this. So there's two kind of diagrams that are of interest. So the first is, okay, I'm a time domain system. I turn it off, so immediately there's this transient electromagnetic wave that's coming. If I looked at the magnetic field, so if I was at Libby's position, for instance, initially I turn this off, it doesn't feel anything. There's a certain time that's required, but then quickly it ramps up to some peak and then just falls down. So this is very different than seismic waves. Seismic waves, there'd be a particular travel time for that wave to get down. So nothing would happen. And then if I had just a straight impulse for a seismic wavelet, it would just be a blip. And then it would go on, there'd be nothing. Diffusive waves behave very differently. Nothing for a while. And then they go up to a peak and then back down. If I was to look at this, take a snapshot at any particular time, now I look at some time after this is turned on, and I look to see what that magnetic field looked like, it would have this kind of a shape. So it'd be 0 at the surface, and there'd be some point at which it would reach a maximum, be at a maximum, and then it would be down smaller after that. This depth at which it achieves its maximum is referred to as the diffusion distance. And it's given by this particular formula here. So the diffusion distance increases with time. Okay, that makes sense. It propagates down. But it decreases with increasing conductivity. So the higher the conductivity, the slower the waves actually travel through. Okay, so that's time domain. So there's another app. It's a plane wave app. You can use either transient or harmonic signals. It's got a 3D volume that looks like this, and you can alter, the frequencies or the conductivities, and then you can look at, in the frequency domain, amplitudes and phase or real and imaginary parts, and just see how everything is propagating it down. Okay, now let's look at the effects of the background resistivity. So we've kind of got this idea that we take energy from our transmitter, we get it here. So we're going to lose energy going down, and we're going to lose energy going back up to our measured responses. So let's do the following. Let's bury a sphere. So here's a conductive sphere. It's going to be in almost essentially free space, 10 to the minus 8 Siemens per minute. And I'm going to look at one particular time, 10 to the minus 5 seconds. And here's the currents. But 10 to the minus 5 seconds, the currents are confined to the outside of that sphere. Okay, so maybe that's a question right there. Like, why? And you can imagine kind of waves coming down, igniting things. Why don't I have currents inside? Why are they just confined to the outside? Anybody?
Because it's a conductor, so charge travel to the conductors.
I'm sorry, so conductor?
The sphere is a conductor.
Yeah.
So charges travel outside the conductor because they are rebelling.
No, not quite. Yeah.
Maybe it's because the decay of the signal after it passes through the chains of meaning.
That has some relevance, but that's not the issue here. If I looked at this at different times, I'd actually see that currents do go in. And eventually they will decay. But the issue here is, okay, why are they like this? Okay, so the clue is that it doesn't matter where you are on here, it's always just the same, right? So it's the same thickness n. And remember, we're at a particular time. Remember also for time domain, what we were interested in was diffusion distance, right? So that diffusion distance depended upon the conductivity, and at 10 to the minus 5 seconds, any electromagnetic wave has only had a chance to go in a certain distance. So it's the diffusion distance that's really controlling. The fact that we're not seeing things at the bottom, that's illumination problems. We just can't get energy. But anything that's here on the top, the fact that it's only propagating in a certain distance is it's a diffusion distance thing, and it's because we're looking at one particular time. Okay, so all right. So now we've been doing all this Falderell perspective. Okay, you got to worry about the background, the attenuation of the energy as it comes in. Okay, I'm going to change that. I'm going to make, instead of 10 to the minus 8, I'm going to make it 10 to the minus 2 Siemens per meter. Now what do you think is going to happen to this picture?
The current density will be lower than the current in that example.
The current density in here will be lower. Why?
Because part of the area will be took by the conductor that surrounds the body.
Okay, so let's change that to 10 to the minus 2. That's what we have. So that picture is almost identical to what we had before. So what happened there?
Too low conductivity.
Correct. So we've got conductivity in here, but the primary energy is not really being absorbed. It's still blasting through here. But if I make it more conductive, make 10 minus 1, now you see what you were expecting to see, right? So now look at the currents in here. So there, you've got currents up at the top, right? You still see some, right? We're seeing through there, but there's a lot of energy that's being lost and a lot of currents that are just in that top. And then if I go one more, if I go to 1 Siemens per meter, that's it. I can't see through that. That's so conductive that all my energy, all my currents are just kind of confined to that top region. Right, so there's kind of interesting visual takeaways here, right? So if we just have completely resistive, we see currents on here. If we have a less resistive, more conductive background, doesn't change, but at a certain point, then the conductivity is high enough that we're starting to get currents that are induced. So that's starting to shield. We could, if you did a geophysical survey and you had, these data, right? So these are, I mean, you're not going to measure these currents, but you're going to measure signals from these currents. You're still exciting this. You're going to see that guy. Here, if that's what you see, there's no hope. You're completely blind.
So, can you estimate? Because I imagine it's a question of amount of energy being transmitted, of the power of the antenna, or it's just a matter of that you cannot see given that little difference between the two conductors.
If you have, there is. Probably someplace between here and here. I don't know, maybe even in here, right? If there might be enough response if you're able to up the power on your transmitter that you can actually start to get through there and maybe see something. But yeah, so generally your depth of penetration is going to depend somewhat on the amount of power, but basically all that comes back down to then is also signal to noise, right? So even if you measure, even if theoretically you could measure something, if your noise is higher than that, you're hooped again anyway. Okay, so that was in the frequency domain, or sorry, in the time domain. What happens in the frequency domain? So what do you expect? Differences, same? So now I'm going to do the same experiment, exactly the same experiment. And I'm going to use a frequency of 10 to the 4th hertz. So we're going to keep that frequency the same. And I look to see what the currents are. So at 10 to the 4th hertz, that looks pretty much the same as our time domain. I'm going to add some the conductivity for the background, make it 10 to the minus 2. Nothing changes. I make it 10 to the minus 1. I get currents up top. I still see that. And if I make it 1, I get that. So time domain, frequency domain, same. So there is the summary for the frequency domain. Okay, so that's kind of what we learned. Let's start looking at some field examples. So here's what I want to cover between today and the first half of tomorrow. So we've already looked at Mount Isa. That was the DC. We're going to go to time domain and look at finding paleochannels for a groundwater problem. In frequency domain, we're going to look for a saltwater salinization problem in Australia. We're going to do grounded sources and be a tectonic problem, Deccan traps, hydrocarbon de-risking. I'm going to talk a bit about marine CSCM and perhaps methane hybrids. We might not actually get to this case history, depending on how much interest there really is. But for the hydrocarbon people, we'll at least do this, and large-scale structures with that. And for geothermal, and from what I understand after talking to Daniel, is that the Icelandic example that we'll show you is actually pretty characteristic to what's going on here. We'll look at Santa Cecilia, which is a Chilean prospect. Reason for doing that is that we have both DC, we'll have control source EMT, and also MT. By the way, this was for an MT system, natural source. Do a synthetic and a real example for ZTEM. For GPR, I'll show you a little bit, but there's one really interesting aspect that has using GPR for self-driving vehicles. And then we'll come back to Mount Isa, because we'll look at that. That's the IP project. And then I want to do something, a case history. I'm extremely proud of what the group at UBC has been able to do with respect to kimberlite pipes and using different kinds of airborne surveys. And in particular, this one uses airborne IP data. So we're able to extract the IP signature from airborne data, invert it in 3D, and use it essentially as a physical property model, combine it with connectivity, density, and susceptibility to get a rock model. So those are the case histories that we're going to do. So what I'd like now to do is to start looking at inductive sources. Any questions while I'm changing slides here?
I have a question. Yeah. I have always been curious about the charge carrier. The charge carrier, the thing with charge that moves through Earth.
Okay.
In different scenarios, there are different charge carriers. How are they? Are they ideology problems, for example? How do you combine the electron part of moving charge to the ion part of moving charge?
I can give you one example that might shed some light. So in groundwater, for instance, one's often interested in, there is the potential for using induced polarization for groundwater, okay? The idea there is that as you move fluids through, you've got forces that are causing, let's say, bound charges to actually move and give rise to polarization charges, which then you can see. There's been quite a bit of work in the, especially in the German community, for looking at IP processes for groundwater, and you look at the imaginary part of that. So that's at least one part that comes about. The other is in self potentials. The example I just showed you for dams. Yeah, so you can build up a charge on those cases too. So there's some connections.
I'm sorry. The principal question is if you have a conductor underground, there are inductive process, so you have currents going down in the target, the conductive target. So there are charges moving there. So there's a part of electrons and a part of ions, cations, anions, etc. So there's a combination of moving charges. So my question is, are maybe one of those most important than the other?
I'm not 100% sure I'm exactly with you in that. So some of those things about anions and cations, those are kind of associated a little bit more with maybe IP and trying to get a signature of that. For a DC resistivity problem, I mean, you actually do have, electrons that are flowing through. So if you followed each individual electron, it's moving, right? But there is a steady state process. I mean, there's an electron that comes in from the battery and then kind of comes around. And so from the point of view of looking at it, nothing looks like it's changed. But at some level, if there's, what was I going to say? Yeah, it doesn't look like there's anything. But if you actually follow that individual particle, it is moving. So in one case, something is moving, but it produces a steady state macroscopic phenomenon. Anyway, there might be a few more things to discuss after we kind of go through. There's two aspects that might be relevant. One is when we do a grounded source, okay, and we're actually going to see both vortex currents in an object as well as galvanic currents. So the galvanic currents are going to generate charges. The vortex currents don't have any charges with it. Those are just simple currents. That might be one aspect. The other has to do with the IP. Okay, so what's our motivation for inductive sources? Well, again, basically what we had just talked about before with respect to large scale, rugged terrain, shielding, whatever. So I'm going to go back and talk a little bit about basic experiment and transmitters and receivers. So again, here you are. You got these are important questions, and you really simply can't get rid of them. They just surface. Like, okay, what is the target, right? What dimensionality, its surface, its depth. And your transmitter, where are you going to put it? On the surface, in the air? Because we can put an inductive source just sitting right on the ground, or we could fly it. And then our frequency domain system, our time domain system. For our transmitter, what's the size of this thing? What's orientation? For exciting the target, we always need to worry about the conductivity of the target and the host, and then coupling. Receiver and data, which fields, what instrument, where to collect the data, how many, how accurate, what's the depth of investigation, what's the footprint of the system. I mean, these are all important questions, and it's why when you're setting up a geophysical survey or thinking about it, you actually need to think very hard about each of these steps, as well as generally do some numerical modeling to see how well you're doing. But I think the important thing is that these things here are really all a question of survey design. So we've just been through that, our basic experiment. Time varying fields, generate currents, generate signal at receiver. What do we have for transmitters? Well, we've got, if you've got large areas or you've got rugged terrain, you really want to be flying something if possible, right? So here's a couple. Here's a resolved system, that's a frequency domain system. And here's a SkyCam system, which is a time domain system. So you have a big loop up here, and you measure receivers here. If you have deep targets, then you've got to get energy down there. That means you need to have a bigger moment. Kind of comes back to something we talked about. One way of doing that, since the moment is the product of the area times the current, you can lay out a large loop. So this is actually a real loop that was laid. It's a couple of kilometers inside. It's in an area in Canada, in Manitoba, and over a deposit called Laylor. So the transmitter, time or frequency, the key factor is moment, current, area, and also you could put in a number of turns. So you could take the same quantity and put in a number of turns. And then your magnetic field looks like this. And the important thing about the your transmitter loop is, even though here's your dipole field, it's falling off as 1 over r cubed. So you've got to worry about that, as well as the attenuation. We just saw that, right? So how much the energy gets attenuated in the ground. You want to be as close to the target as possible so that your best shot might be a ground-based system. Otherwise, helicopters, your next best, or fixed-wing aircraft is next, and you're always worried about coupling. Receiver and data, we just went through this. You could measure the B fields with flux gate or dB/dt with coils. So if we look, let's first of all look in the time domain. So the good thing about this is that there's no primary field. And so you just measure the secondary responses. And the receivers could be mounted on a transmitter, as they are here, or they could be mounted above the transmitter. Or here's a case, and if people are interested, I might show this example. It's a case history over that Lalore deposit. So there is it's an inductive source, large loop, so it's a couple kilometers inside. And it's a time domain experiment. And then the data are actually flown from a helicopter, and they're measuring the total magnetic field. So now you're actually measuring the total magnetic field with cesium vapor magnetometer. The frequency domain, the challenge there is the primary field is always on, and those primary fields are large compared to the secondary fields. You just have to do something about them, and you've got some options. You can try to compute what that primary field is and subtract, which means you need to know geometries really well. Or a lot of times they'll introduce what's called a bucking coil. So you've got a primary flux that's coming from your transmitter. So if you had another little coil out here that gave a magnetic flux that was equal strength and opposite direction to the primary, then you kind of cancel that out, and then the only thing that you measure is just the response of the ground. So a lot of systems actually use that. The key requirement in all these is you really need to know where the transmitter and receiver are, and often keep them in one unit. Here's that resolve system. So it's got coil pairs. So each of these is a coplanar coil, right? So it's sitting on one plane. And this is a transmitter, and that's a receiver coil. And then you've got these 5 different coils giving at 5 different frequencies. And then you could also change the configuration of the coil, so you could have coaxial. So there's one like this. How many people have seen an EM31? Is that common here? Anybody? Yeah. So this is one of those. It's used a lot by engineers, especially in site characterization. It's good only for the top couple of meters of the ground, but it's a loop system. Just sort of wander over the ground. Operates at a single frequency, about 10 kilohertz. So now we sort of these questions of depth of investigation and footprint of the transmitter. So let's see how we might even kind of address these things. We're going to look at a time domain. So we've got a few things here. We've got current that's on, and then we're going to shut it off, and then look at the response. So the response, if we're measuring B, would look like this. If we had dB/dt, there'd be an impulse, and then look like that. What you're going to see now is a sequence of images that really have to do with the currents. Your understanding about what's happening in a time domain system or frequency domain is like, okay, where's the currents, right? Because if there's currents, then you know you're somehow sensitive to that part of the body. So what are the currents that are seen? And we're just going to step through just a simple example. Start with just look at a homogeneous Earth. So we're going to take an Earth. The dashed line is the surface of the Earth. There's going to be a transmitter 20 meters above, and it's a VMD, vertical magnetic dipole. Like a horizontal loop, right? It's going to give a vertical dipole. That's why it's called VMD. The region underneath is a half space, 100 ohm meters. And this is where what we're going to be looking at is where are the currents, how strong are they, and then what are the resultant magnetic fields look like. So we do a vertical magnetic dipole over here. There's going to be two plotting planes that we have. So one is a cross-sectional plane, and the other is on plan view. So first of all, let's think about the currents. Which direction? So we got a transmitter, right? It's got a loop, right? And if we turn that off, there's going to be currents in the ground that should have that same symmetry. So the currents are also going to be circular, and that's what this is showing. So this is a plan view of the currents, and you can see that they're all circular. The currents, after we've turned them off, are distributed in the Earth in a following manner. So at a particular time, 0.01 milliseconds, the currents are coming out of the board here and going into the board here, so they're kind of circular like that. But you can see that there's a large distribution. Okay, so given that those are the currents, what are we going to expect for the magnetic fields? What are the magnetic fields going to look like?
Going to point upward.
Going to point upwards. And where is the strongest magnetic field going to be?
Right in the middle to the solution.
Each of these things is like a little circular filament, right? So then that gives rise to a magnetic field that's like that. So if you're sitting right above here, those magnetic fields are all going to be up like this. If you're sitting up over here, they're going to have both a vertical and a horizontal component. The maximum strength of the magnetic field, just on kind of first principles, should actually be probably someplace in here, right? Because that's where all the currents are. And in fact, that's it. So if you plot the magnetic fields, that's what they look like. And so up here, yeah, they are going pretty much horizontal. And if here's our receiver sitting up here at that red point, yeah, we're definitely seeing magnetic fields that are coming from that. So now let's think about how things propagate through time. So this is a very early time. And the diffusion distance, remember we had that formula, so the diffusion distance says at this particular time, it's 18 meters. I've turned the transmitter off. I've got these circular currents in here. They've got this distribution, and 18 meters is about this point here. So we've got a number that's kind of related to what that picture is as far as the currents. And magnetic fields look like this. So let's concentrate on the currents. A little time later, diffusion distance is 38 meters, but look what's happened to the currents. They've kind of diffused down. A bit later, like that. Later, like that. So if we look at those things together, these are early times, later, and later. You see that the currents, which initially kind of started underneath the transmitter loop, are kind of going down and outward. I don't want you to be misled by these colors. The color scale is changing a lot, but I mean, in order to portray anything, we can't plot things on the same value. But this is 10 to the minus 7, that's 10 to the minus 8, that's 10 to the minus 9. So the yellow is continually decreasing in amplitude as we go down. The thing that's kind of interesting about this is that Misak Navigian wrote a very seminal paper, in 1979, because people were trying to understand, like, okay, how do I understand the magnetic fields from these time domain experiments? And he did some mathematical analysis and showed that as a function of time, the current concentrations kind of go like this and, operated. And effectively, you could think about the response as being due to a smoke ring, which is a circular current that's kind of diffusing up. So, if you have a cigarette, not that anybody smokes cigarettes anymore, but if you remember people who smoke cigarettes, right? They take a big puff of smoke and then you go make a little cloud and then it just goes out. And so it's like a smoke ring. So what's our important points here? Well, first of all, the currents are going to flow in the same plane as the transmitter. Currents are going to diffuse downwards and outwards. Each transmitter has a footprint. And if people always ask about resolution. Okay? That's always the first thing anybody asks. What's the resolution? You could get some idea about resolution simply by looking at where your currents are. So your best time resolution is actually going to be at the very earliest time channel. And at the very earliest time channel, if your currents are concentrated in something like that, you're going to get some idea that, okay, I've got, whether my object is here or here, I'm not ready to see very much everything. But you get some sense about the scale of resolution that you can get out by looking at the currents at the earliest time. And the latest time, where your currents are at the absolute latest time, that's giving you some insight about the depth of investigation. Because you're going to see responses from currents at any particular time. And if you find that currents are sitting out here, then you can say, well, I'm at least seeing down to that. So just knowing the currents kind of gives you at least some idea about where you are with respect to things. Okay, where are we? Okay, so let's do something that's just a little bit more interesting. Not that that wasn't interesting, but okay, we're going to take this Earth. That was a half space. Okay, everything is the same, except we're going to put in a layer in here that's 20 meters thick, and we're going to change its resistivity. We're going to make it resistive, and then at 1,000 ohms, and then we'll make it conductive. So the question is, what are we going to expect? Okay, so let's first of all look at the background. So here's our half space. That's what the currents look like. Suppose I, between 20 and 40 meters, put in a resistor. What do you expect is going to happen to the currents? Anybody? Pardon me?
Smaller.
Currents get smaller? Same? And where do the currents get smaller? Anybody else? Okay, just even if you got a good answer, yeah, go ahead.
Well, in the resistive layer, it's going to be less currents, and you're going to get in the medium. If it's more conductive, it's going to take a lot of the currents.
Okay. Okay. So if I make it resistive, this is actually what happens. So the currents here. So you were saying that you're going to get fewer currents, and you do. Right? You get fewer currents that are going in here. Interesting enough, you actually get more current that's coming down here. So, because you're not attenuating anything. So the fields are coming down through here. There's not so much attenuation, and you're getting actually a little bit more current. Okay, and now we make it a conductor. So now we'll come back to, if we take that and make it a conductive medium. If we do that, then now you see, oh, my major currents are actually in the conductor. So there's electric fields everywhere, right? But here's where the major currents are. And if I make it very conductive, now I'm not even seeing through this conductive layer. Everything is just sort of right up at that top. So again, it's working exactly, I think, how you might intuitively think here. The electromagnetic conduction is not affected by a resistor. Just kind of go blasts through. Whereas it is, if we have a conductor, greatly affected by it. And this is why the reason that inductive source geophysics is great for finding conductors. It sucks to find a resistor, right? But it's good for finding a conductor. So what do those fields look like in each of these cases? Well, we look at the fields, and you can see they kind of get, the fields are all kind of distorted. And notice the magnetic field down here is actually larger than it was. We're still up here. Here's our receiver. We can still see something. What's really perhaps more informative, and this is the way people would generally plot things, is actually plot the sounding curve. So what we've got here is a background resistivity of 100 ohm meters. Here's the curve that you get. If you put the resistor in, then that resistor, here's the layered earth. You know, there is a little difference, but it's pretty subtle. If you put a conductor in, now you get a very large difference between the background and this. And if you put a 1 ohm meter, it's like huge. Okay. So this again is telling you that you're with an inductive survey, you're just going to be much more sensitive to try to find a conductor than a resistor. So here's the airborne example. So what we've got is a sphere. Now you're going over this with your inductive system. At very early time, you're really sensitive just to what's happening up at the surface. The waves haven't had a chance to diffuse in. So your data in plan view in a map would look like this. So what we're looking at here, these are the locations of the individual sounding points. And at this particular time, 0.025 milliseconds, everything is pretty much the same. I'm going to draw a profile along here, and here's the values here. So they're all the same. You're just seeing the background half space. I look a little bit later. Now these waves have had a chance to diffuse in. We're starting to ignite the sphere. And you can see that in plan view, I've got something that's coming up here, and a profile like this. If I look later, still this is kind of the sweet spot, 0.3 milliseconds. I've got a nice anomaly here, and here's my profile. A bit later, now everything is starting to decay. So I had currents into my conductive sphere, but they're dissipating energy as they travel, so they're going to decay away, and eventually I'm back like that. So here's a summary. Plan view maps as a function of time would look like this. There's one particular time, it's a bit of a sweet spot. In profiles, the earliest profiles don't tell you anything, they're just your background. The anomaly, and so these are amplitudes, right? So these are orders of magnitude. So notice the scale yeah, it's 10 to the minus 5, that's 10 to the minus 11. That's 6 orders of magnitude change in that signal strength. So that's huge. Nevertheless, as profile view, you see that there's some bumps there, and that's indicative of that conductive sphere. So a time domain system, there's a ton of them out there. They all kind of work on more or less the same principle. So here's the SkyTem system. It's about 300 square meters. It's about 30 meters across. And they have two things. They've got a high moment system and a low moment system. So the high moment system has a current peak of about 90 amperes. So notice, remember that the moment was the product of the area times the current times the number of turns. So this has got 4 turns, 90 amps, and yeah, big moment. This one has got only 40 amps and 1 turn, so it's got a much less moment. Why do you care about that, or why? What's the deal here? If you have a high moment system, you crank it up. What you really want to do is you want to truncate that thing immediately, but you can't. You got so much back EMF that you try to turn it off in a ramp, and you try not to get any current in the primary loop that's going on in this. And the best that you can do is kind of a shallower ramp, and then an early time of about 47 microseconds. If you have a lower moment system, then it's possible to turn that power off and the current off much more quickly, and you can get back to maybe 12 microseconds. For each of these, there's a waveform, just like this, cut off, and then that. And then you can measure it a whole bunch of individual time changes. And this lower moment system is a bit different. You can turn it on faster, you could turn it off more rapidly, and then it would have its own time channels. There's a couple of things that, well, I'll just make one more thing. If you have another system, here's a VTEM system. So here's your transmitter loop, here's your receiver loop, so now it's coincident in the center, and here's your waveform, kind of comes up like that, goes off, and then is measured along here. So there's a few things that are really important about this, and this comes back time and time again, irrespective of what survey is being done, and that is, what is the current that is actually in that transmitter? What really is that current? So you need to know, if you're going to do some high quality work, you need to know exactly what this waveform is, what the ramp is, where t equals 0 is, all of the details of that. It hasn't been until a few years ago that contractors were really kind of providing some of that stuff. Actually, Terry, is one of the things that you guys did really early on. I remember it was at ASEG where you were, I think, comparing what the waveforms were from these different instruments, and they were just like all over the map. They're supposed, they said, oh yeah, we got a kind of square wave or something, but they weren't close.
I ran about that.
Yeah, but still, it's the same issue, right? You need to know what current is going into the ground. So if you're ever contracting things out, have to make sure that this information is known. Contractors are getting better and better, and it will not be long in the future before every sounding that you have is actually accompanied by what the waveform is. That will come. So let's do a case history. I like this case history for quite a few reasons. Not only for what information it shows how you can get good information about Earth from airborne inductive surveys, but also what the electrical conductivity structure was in the whole process as part of a long-term goal for groundwater hydrology. So the bottom line is that here's kind of a simple geologic representation of what's going on. The area is in Denmark, so up in here, and here's a local survey area. We've got a base of Paleogene clays, and then we've got sort of these incised, kind of tooth-like things that include both gravels, tills, sands, and a few odd clay layers. So that's kind of the background. The groundwater is housed in these incised structures, and what they really want to know is, suppose you had a well here and you started pulling stuff out. Okay, you're pulling water out. Where's it coming from? Pulling out here, is it coming from right around here, from the north, from the south? Where is it? And similarly, if you had another well over here, and you started drawing it out, like, are those two wells talking to each other? Or where's all the water coming from? So that's kind of an interesting question, and one that geophysics can play a role at. So first of all, you need to decide, okay, what are physical properties? So you've got all of these different rock units, and the bottom line is that the coarse sands and gravels, okay, are fairly resistive, so they're 40 to 60 ohm meters, and the clays that you've got, these Paleogene clays underneath, are really pretty conductive. They're like 1 to 10 ohm meters. So it's basically a matter of finding the top of a conductor underneath a sequence of more resistive material, and that's basically it. That's ideally suited to an inducted source experiment. The one that was chosen was the SkyCam. So here's that transmitter I showed you a little bit earlier. Here's the receiver that they've got. So it's mounted right on the side so that it's null coupled with the primary field. And they have the high moment system, look like that, and then the low moment system. So the high moment is, of course, used to see deeper. The low moment is going to tell you more about what the dimension of the structure is. So the data, the blue lines are the lines of acquisition data, about 300 odd line kilometers, 10 meter spacing. And there was some noise, so they got rid of some of the data points because of that. Ended up with this. About 9,500 soundings, and they inverted them kind of with a 1D inversion algorithm, but making them kind of laterally constrained so that, if you're sounding here, it can't be really discordant from its neighbor. They have to be connected somehow. So there's sort of a spatial averaging, and that's actually becoming quite popular. It has been popular for quite some time. And sometimes it's called a quasi-3D approach. So what do we see? When you do that inversion, put them all together, and you look at a depth slice that's 5 meters above sea level, then this is what you see. So the blue stuff is really resistive. Oh, sorry, the blue stuff is really has low resistivity, and the reds in here have a very, very high resistivities. So these are going to be your kind of Paleogene clays, and these guys here might be your incised bites that you want. That's a little bit more apparent in this one here. So this is now the elevation to the top of the Paleogene clay. And the blues in here are indicating very deep incisions, and the reds are shallow. So here's your basic primary kind of water patterns. They work with that, and then they actually kind of divide it up into more or less like 20 odd structures that were there, buried valleys that were primarily the conduits for the water. Then they did one more thing. So that gives you the depth to the top of the clay. So now you've got that. But then there was a few places that they actually did borehole analysis. So they drilled and they looked at what the electrical resistivity was as a function of these different units that were in. Then they took the conductivity model and used that as a proxy then for extending these same units elsewhere. So now that gives you kind of a geologic model, but you also know the hydraulic conductivities of each of those units. So now you develop a 3D hydrogeologic model with the hydraulic conductivity. So that allows them to do the following. So now they take that 3D model and they put it into something like ModFlow, which means that, okay, if you've got a hydrogeologic model and you're forcing water out here, or you're pulling water out here, or pushing it in here, that you can actually figure out where things are flowing. And that's what they did here. So they had a well here, it was pulling out a well here, and then you could see, okay, the water from here is kind of coming from this region in here rather than from that, and then the same here, and maybe there is some kind of crosstalk there. So I think that was a really nice example for how you go from an airborne time domain system, invert it, and eventually work and get a 3D hydrogeologic model out that is useful. I'm not going to talk in depth about this, but there might be some people who are interested in just a few things. We can talk more about this later. This was work that was done in Saudi Arabia by a guy named Daniel Colombo. He's a very good electromagnetic geophysicist, and he's been working now with Saudi Aramco for a number of years, and he's been developing a lot of in-house structure for jointly inverting different types of data, in particular EM data and seismic. That's kind of a holy grail for a lot of things. And the problem with, so here was the area. It's in the Gulf, and there's a section that was inland here, and it's got some real problems as far as the oil industry was concerned. And the problems are really the following: that you have either sand dunes, or you have some karst, or you've got body, and it just screws up the seismic. So what the seismologists want to do is to make a better, get a better velocity model so that they can get better statics for doing the processing. And so this was all about trying to develop a better velocity model and do a joint cooperation. So the bottom line was that there's a lot of faults and various kinds of things in there that you need to take account of. And they thought, well, they'll do a time domain EM survey. They compared airborne work to ground work, and they found they've got the same apparent resistivity curves. Here's an interesting map. So here's an apparent resistivity map at a particular time channel. And then here is a seismic time slice. So you just look at those two things and you say, wow, those are pretty good. I mean, there's certainly major features of these two things that are the same. So that opens up the concept of somehow working with these two things jointly, either formally or in some ways. And Colombo does it in a couple of ways. But the one thing that was particularly interesting was, in coming back here, was to use the EM information and this as being co-located for structure. What I mean by that is that, let's suppose I've got two physical properties. I've got seismic velocity and I've got electrical resistivity. Okay. If the seismic velocity increases, I don't know whether the EM conductivity should increase or decrease. Similarly, the other way around. However, what I might expect, and that is coming from this picture, is that if if the seismic velocity changes at some point, then perhaps the EM conductivity is also going to change at that point. In other words, there's going to be a structural correlation between the changes. So that's something that's used more and more these days. It's kind of like joint inversion with structure. And this picture kind of forms the basis for why that happens. And yeah, so in the end, what they did was do a 1D inversion, well, this quasi 1D inversion with the airborne time domain data. And they got a conductivity model, and they put that as input into a joint inversion with structure, with the seismic data being tomographic data. And then got a better seismic velocity, hence better static corrections. So, yeah, how they do that, need to know. Anyway, that's an interesting. It's an interesting case history. If anybody is interested, you can go through that. And so my guess is that we should probably about break for lunch, right? So I'll tell you. I'll tell you what's going to happen. We're going to pick up inductive sources right after we come back from lunch, and then we'll do the grounded sources, which has got a number of applications. And that, between those two things and some case histories, will probably take up the rest of the afternoon. And then tomorrow morning, we'll pick up the other stuff. So with that, let's break for lunch and be back by 2 o'clock.